Welcome to The Sleepy Scientist. It's wonderful to have you here tonight. Before we begin, I'd love to know, where in the world are you watching from? A quiet bedroom with the lights low? A peaceful train ride home? A cozy corner where the day is finally loosening its grip? Wherever you are, I hope you're comfortable and ready to settle into something calm and unhurried. If these gentle explorations help you relax, a like and subscribe would mean so much, and to those already subscribed, thank you. Your support keeps this quiet little channel drifting steadily through the cosmos. Please also tap the notification bell so you never miss the next slow voyage into the night. I'll try not to make this evening's topic so interesting that it keeps you wide awake, but if it does, at least you'll drift into the later hours knowing a great deal more about a world where sunlight arrives as only the faintest whisper. Not the worst reason to be up a little longer. So, shall we begin? What secrets wait inside a planet so distant, so cold, and yet so unexpectedly alive? The universe grows quieter the farther you travel from the sun. Warm light fades into a soft, dim glow. Hours pass before a single ray reaches the distant frontier. And circling out there in the slow, cold dark is Neptune, a deep blue world shaped by forces far more dramatic than its peaceful appearance suggests. Its winds race faster than sound across cloud tops the colour of twilight. Its atmosphere hides shifting storm that form and vanish like passing thoughts. Heat wells up from deep inside, even though the sun offers almost nothing in return. Rings made of dark, delicate dust circle silently around it, nearly invisible unless the light strikes just right, and moving in a retrograde path as if pulled from another life entirely is Triton. A frozen moon with geysers, mysteries, and perhaps an ocean sealed beneath its crust. In the stillness ahead, we'll explore Neptune's discovery through mathematics, the colours that shape its blue glow, the strange physics inside its mantle, the storms that sweep across its surface, the moons that drift around it, and the role this distant planet plays in understanding worlds much farther away. There's no rush, no need to catch every detail. This journey moves slowly, opening each idea with the gentle pace of a long exhale. So settle in, let your thoughts soften, and allow the distant blue of Neptune to rise into view. Uranus was meant to move with the quiet certainty of a distant clock, tracing its wide, pale blue path around the sun in a rhythm so steady it should have felt almost serene. For many years, that seemed to hold true. The planet drifted along its orbit with the slow confidence of something that had done the same thing for billions of years. But as telescopes improved and astronomers sharpened their measurements, something faint and persistent began to whisper through the numbers. Uranus was not exactly where it was supposed to be. At first, the differences were so small that most observers would never have noticed them. A fraction of a degree here, a tiny shift there, variations so delicate they could have been blamed on a shaky hand, a cold night, or a moment of unsteady air. But the astronomers who watched Uranus most closely began to notice that the deviations were not fading away with better instruments. In fact, they became clearer. The more carefully the sky was measured, the more the planet insisted on telling the same quiet story. Something was tugging on it. The idea that Uranus was being influenced by an unseen presence emerged slowly, almost reluctantly. Astronomers are trained to distrust coincidences and to question anomalies. They check their tables. Then they check their previous checks. They recalculated the orbit using different assumptions. They traced the planet's path across older charts, comparing handwritten logs from decades earlier to new observations made with improved lenses and cleaner glass. None of these efforts made the wandering disappear. Uranus kept arriving a little too early at one point in its long orbit, then a little too late at another. Imagine watching a pendulum that swings almost perfectly, but each time it reaches one side it is ever so slightly off from where it ought to be. Over one swing, the error is barely noticeable. Over tens of swings, the difference becomes undeniable, and over hundreds, it becomes impossible to ignore Uranus was revealing a pattern, but only to those patient enough to listen to its quiet irregularity. Astronomers tried explaining the anomaly by adjusting the assumed mass of Uranus. Perhaps the planet was heavier or lighter than expected that would affect its motion. They tried modifying the gravitational constant, wondering if the accepted value might be marginally off. They even considered whether the Sun itself might be shedding mass in a way not yet understood, but none of these explanations held. Each adjustment fixed part of the problem, but not the whole of it. The numbers still refused to behave. Slowly, a new idea began to settle into the collective mind of the astronomical community. If Uranus was being pulled, then something had to be doing the pulling, something large, something distant, something that had not yet been seen by any telescope on Earth. A world beyond Uranus, exerting its presence not through brightness or beauty, but through gravity alone. This possibility was both thrilling and daunting. It meant the solar system was not yet fully mapped. It meant there were still places in the darkness where a planet could hide, circling the Sun in a zone so far away that sunlight took hours to reach it. And most importantly, it meant that mathematics, quiet, meticulous, stubborn mathematics, could reveal a world long before a human eye ever glimpsed it. The deviations in Uranus's orbit were not random. They followed a specific waveform, rising and falling over decades in a pattern that mirrored the imagined position of an unseen companion. The planet seemed to lean slightly outward at moments when the invisible mass was predicted to be ahead of it, and fall slightly inward when the unseen world lagged behind. It was as if Uranus were dancing with a partner hidden behind a curtain, responding to a pull it could not refuse. Plotting the deviations over time revealed a graceful but unmistakable signature, a gravitational fingerprint, a message written not in light but in motion. And though the telescopes of the early 1800s were good, they were not good enough to see that far. The unknown planet lay deep in the outer cold, far beyond the reach of the lenses of the era. Yet it was there, its presence felt in the wavering path of Uranus, like an echo heard before the sound itself. Imagine the determination required to follow such a lead. Not a bright spark across the sky, not a sudden discovery, but a trail made of the faintest discrepancies, a planet calling out through mathematics alone. Night after night, astronomers sat in chilly observatories comparing columns of figures, adjusting angles, recalculating positions, waiting for the universe to yield its secret. Every new measurement sharpened the picture, tightening the margins until the answer became too clear to deny. There is a kind of magic in watching the invisible become real. A world no one had ever seen was announcing its presence through the smallest of gestures, influencing another world's orbit with such delicacy that only the most dedicated observers could catch it. Uranus played the role of a messenger, its soft deviations forming a pathway into the unknown depths beyond. For astronomers working in those years, it must have been extraordinary to realize that they were not just studying Uranus, they were being guided by it. A distant giant was quietly pointing toward an even more distant one. Each anomaly in the orbit was another step along the trail, another clue, another nudge outward into the frontier of the solar system. This subtle drift, this tiny gravitational whisper, carried within it the first hint that Neptune existed at all. Long before its deep blue face was ever seen through a telescope, long before its rings and storms were discovered, long before its name was chosen, Neptune was already shaping the motion of Uranus with a consistency that no amount of recalculating could erase. Its gravity reached across the darkness, leaving a delicate mark on the orbit of a neighbouring world, waiting patiently for the moment when human curiosity would follow the trail all the way to its source. In the gentle wandering of Uranus, in the soft discrepancies recorded over decades, the universe was offering a quiet invitation, a signal, a suggestion that there was more out there than anyone had yet imagined. And in time, that invitation would lead directly to the discovery of a world unlike any known before, a deep, distant sphere of blue waiting in the cold, its presence hidden not in light but in the elegant language of gravity itself. The drift of Uranus had whispered the presence of something hidden, but whispers alone could not reveal a world. To uncover the source of the mysterious pull, astronomers needed more than careful stargazing. They needed to read the language of gravity itself, and so two mathematicians on opposite sides of Europe began to follow the invisible thread. One was John Couch Adams in England, and the other was Urbain Le Verrier in France. They had never met, never spoken, and yet both found themselves staring at the same puzzle. If Uranus was being tugged by an unseen planet, where exactly was that planet hiding? Adams approached the mystery with a kind of quiet intensity. Born with a natural gift for mathematics, he carried the puzzle with him like a melody that refused to leave his mind. At Cambridge, he combed through tables of Uranus's observed positions, charted over many decades by astronomers who had watched the sky with so much patience. The numbers told him everything he needed to know: when Uranus arrived early, when it arrived late, how far off course it seemed at different points in its orbit. Those changes were subtle, but they were not random. They formed a gentle sway in the planet's motion, like a curtain being tugged from behind by a breeze you cannot see. That breeze, Adams believed, came from a distant world. He began constructing equations that linked Uranus's motion to possible orbits of the unseen planet. If the mysterious body was farther out, its pull would be weaker. If it was heavier, the tug would be stronger. If its orbit was tilted, the effect would shift the deviations one way. If not, they would shift another. Every assumption created a slightly different world. Adams tested each one, adjusting the planet's position, its mass, its distance, its inclination, narrowing the possibilities as though sanding down a piece of wood until it fit smoothly into place. Night after night he filled page after page, and slowly the possibilities collapsed into a single elegant answer. The new planet should be found in a very specific region of the sky. Adams sent his prediction to the Astronomer Royal, but the communication faltered. The idea seemed too bold, too reliant on theoretical mathematics. In those days, the notion that one could locate a planet without first glimpsing it through a telescope felt almost like a magician's trick. The message was not acted upon. The cosmos was not yet ready to reveal its secret through Adams. But elsewhere, the same secret was beginning to take shape in another mind. In Paris, Urbain Le Verrier approached the mystery with a very different temperament. He was meticulous, methodical, unyielding, a mind built for precision. Where Adams worked quietly and privately, Le Verrier pursued the problem publicly, sending his findings to the French Academy of Sciences and updating them regularly. Step by step, he stripped away the possible errors, tightened the equations, and refined the unknown planet's predicted location. He treated the deviations in Uranus's orbit as clues left behind by a celestial visitor, tracing them with the exactness of a scientist dissecting a mathematical heartbeat. To explain the concept, imagine pulling gently on a boat's anchor line. The boat moves just a little, drifting off course. Now imagine that the boat is Uranus, and the anchor line is the gravitational pull of a far-off world. By measuring exactly how the boat shifts, how quickly, how slowly, how often, you can reconstruct the movements of whatever is connected to the other end. You may not see the anchor, but you can chart its presence through the boat's subtle dance. That was the essence of orbital perturbation, and Leverrier mastered it. By the late summer of 1846, he had finished his calculations. He knew where the new planet should be. He knew how bright it ought to appear. He even estimated its distance from the Sun. The confidence of his prediction revealed the depth of his work. This was no tentative suggestion. It was a statement of conviction. The numbers pointed to one slice of the heavens, and Leverrier trusted those numbers completely. On the 23rd of September, he sent his prediction to Johann Galle at the Berlin Observatory. Galle received the letter on the same day it arrived. The sky that night was clear. The telescope stood ready. And so, instead of waiting for confirmation or debating the boldness of the claim, he simply pointed the instrument toward the coordinates Leverrier had provided. The task now was not to find a bright, obvious world, but to spot a faint point of light that did not belong. Stars keep their positions. Planets wander. If Galle could find a point that drifted over the course of hours, their planet would be revealed. He compared the view in the telescope to the star chart, one dot at a time. Most of the lights matched perfectly, and then there it was, a point of light that should not have been there. A pale, distant glow that did not appear on the map. It was faint, steady, and unmistakably out of place. Galle observed it again later that night. It had shifted. The discovery was immediate, almost shockingly simple compared to the decades of quiet drift and the months of intense calculation. With a single night's observation, the invisible world stepped out of hiding and confirmed everything the mathematics had suggested. The unknown planet was real. It is difficult to imagine the feeling of that moment. A world beyond the edge of sight had been predicted on paper, summoned into awareness not by the eyes but by the mind. Before any telescope found it, numbers had already drawn its outline. Equations had already traced its orbit. Gravity itself had already sent its message through the slow drifting of Uranus. Neptune had been discovered through silence, through the gentle pull of one world on another, carried across unimaginable distances until its presence could no longer be ignored. It had been found by listening to the sky, not with the ears but with mathematics, and when Galle finally saw it, the universe seemed to say what the equations had whispered all along. The hidden world was always there, waiting patiently for someone to follow the clues written into the motion of the planets. Neptune drifts through a realm so distant that the familiar warmth of sunlight becomes almost unrecognizable. While Earth circles the Sun at a distance that fills our days with brightness, Neptune orbits nearly 30 times farther away, wandering through a region where light fades into a soft and silvery glow. If you could stand on some imagined vantage point far above its cloud tops, the Sun would appear not as a blazing disk commanding the sky, but as a pale star, bright enough to cast shadows, yet gentle enough that even the sharpest midday never rises beyond a kind of cosmic twilight. The sheer scale of that distance is difficult to grasp. Sunlight that reaches Earth in just over 8 minutes takes more than 4 hours to reach Neptune. By the time those rays arrive, they have thinned, softened, and cooled, stretching across the vast emptiness of space until all that remains is a faint whisper of warmth. Even at what would be local noon, the light would seem muted, as though filtered through a delicate haze. The colours would be subdued, the shadows mild, the sky tinted by the deep blue of the planet's atmosphere. It would feel like standing on the edge of a dream, where everything is real but softened by distance. In such a remote orbit, Neptune moves slowly. Its path around the Sun is so vast that it takes nearly 165 Earth years to complete a single loop. Generations come and go on our planet, while Neptune is still tracing the same arc through the darkness. When Neptune last returned to the place where it was first seen through a telescope, more than a century had passed since that moment, long enough that the astronomers who discovered it had lived entire lives while the planet advanced only a fraction of its journey. Time behaves differently out there. It stretches, relaxes, unwinds itself. If Earth's seasons feel stable and cyclical, Neptune's unfold with glacial slowness. A single season can last more than 40 Earth years, passing not with sudden shifts, but with broad, sweeping changes so gradual that they could go unnoticed in the span of a human lifetime. Imagine winter lasting long enough that no one remembers its beginning, or summer stretching across the years in a slow drift of pale light and shifting shadows. On Neptune, these transitions are measured not in months but in decades. The Sun's distant glow is not entirely without influence, however. It still guides Neptune, holds it in orbit, and marks the rhythm of its slow year. But the grip is gentle, like a far-off lantern whose light reaches you only after a long and wandering path. The soft illumination never harshens, never blazes, never pushes away the darkness. Instead, it leaves the world cloaked in calm blue tones, where brightness feels more like a memory than a guarantee. From such a distance, the familiar architecture of the solar system begins to appear smaller, more fragile. Earth, Mercury, Venus, and Mars shrink into a cluster of inner sparks. Even Jupiter and Saturn draw closer together, sharing the inner half of the Sun's domain. Neptune resides in the outskirts, where the gravitational pull weakens, the stars appear a little sharper, and the emptiness between objects stretches into quiet expanses. It exists in a place where the crowding of the inner planets gives way to spaciousness, where objects drift apart like islands scattered across a vast ocean. Picture gazing upward from Neptune's upper atmosphere. The stars would seem unwavering, crisp, and densely packed across a sky untouched by many of the distortions that affect closer worlds. The faint sun would hang low and small, not much larger than a bright star. The light it casts would be enough to reveal the curves of clouds and the edges of storms, but not enough to bleach the sky or chase away the planet's deep blue hues. Twilight would be the default state of the world, a gentle half-light that wraps itself softly around everything it touches. This pale illumination shapes Neptune's atmosphere, influencing the way clouds form, storms gather, and the upper layers reflect colour. The sunlight that does reach the planet interacts with methane in the air, painting Neptune's surface with the rich sapphire shades that make it so distinct. Yet even this colour appears subdued when compared with the brilliance of closer worlds. There is a softness to Neptune's blue, as though the planet is wrapped in veils of light that travel thousands of millions of kilometers only to arrive in a faint, delicate wash. Living under such faint sunlight would change one's sense of time entirely. Sunrise would arrive in slow tones, barely brightening the horizon. Noon would feel like late afternoon on Earth, with the sun never quite managing to dominate the sky. Sunset would not be a dramatic drop into darkness, but a gentle dimming, as though the world were slowly exhaling the last of the day's light. The transitions would be smooth, unhurried, and atmospheric, like watching the world drift through shades rather than boundaries. Neptune's immense distance also affects how it interacts with the rest of the solar system. Its gravitational influence reaches outward into regions filled with icy bodies, comets, and debris left over from the formation of the planets. But despite its size and mass, Neptune does not rule this domain with the authority of Jupiter. Instead, it guides more subtly, shaping orbits and nudging objects into resonances that unfold over centuries. The idea of living through a single Neptunian year invites a kind of reflection on scale. If you were born at the beginning of one year and lived an entire human life, you would not see Neptune complete even half of its orbit. The planet's seasons, storms and changes all take place in a tempo that dwarfs human timelines, and yet this slow movement feels fitting for a world so far from the sun, where light takes hours to arrive, and the space between moments stretches with quiet grace. There is a calmness to such a world, a patience. Neptune's orbit carries it through regions where darkness is not something to be feared, but simply part of the environment. The thin sunlight is steady, not dimming further as it moves. Once you're accustomed to the gentle radiance, it becomes just another feature of the landscape. The planet circles the sun calmly, steadily, unhurried, following a rhythm set billions of years ago. Out there in the distant reaches, time does not feel rushed. It lingers, stretches, breathes. Noon resembles twilight, seasons last lifetimes, and the sun glows like a soft lantern guiding a wanderer across a wide, quiet sea. Neptune's home is not just distant. It is peaceful in a way that the inner planets will never quite understand. Neptune carries a colour unlike any other world in the solar system, a deep, velvety blue that seems to glow from within, as though the planet has absorbed the quiet of the outer darkness and turned it into pigment. The source of that colour begins with something simple, something found in small amounts in the atmospheres of several planets: methane. In Neptune's upper layers, methane molecules float through the cold air and do something remarkable. They drink in the red wavelengths of sunlight, absorbing them before they can scatter into the sky. What remains is a palette tilted toward the shorter wavelengths, the blues. These blues do not simply illuminate the planet, they become the planet's identity, washing across its cloud tops like the surface of a calm, distant ocean, lit only by a winter sun. Sunlight that travels to Neptune has already lost much of its intensity. By the time it reaches the planet, it is a faint, softened version of the radiance that warms Earth. This dim, cool light interacts delicately with methane, which refuses to let red photons pass, but lets blue photons scatter like drifting sparks. That scattering creates the planet's overall hue. But what makes Neptune's colour so striking? More intense than Uranus's soft turquoise, deeper than any earthly sky, is the way its atmosphere shapes and enhances the effect, layer by cold layer. Neptune's atmosphere is not a simple blanket of gas. It is a multi-layered structure, with different materials and temperatures stacked in slow, swirling bands. High above the cloud tops lie thin hazes composed of tiny particles. These hazes form when sunlight breaks apart methane molecules, creating a cascade of chemical fragments that ultimately join to make fine droplets suspended in the air. These droplets scatter sunlight in different ways depending on their size and composition, adding softness in some places and sharpness in others. They help turn isolated blue light into something richer, more spread out, more luminous. Below these hazes sit layers of methane ice clouds, pale, ghost-like formations drifting in the planet's upper troposphere. When sunlight filters down to these clouds, the effect becomes even more dramatic. The clouds reflect the remaining light back upward, but because so much of the red has already been absorbed, the reflection takes on a saturated blue, as though the clouds themselves are steeped in colour. The cycle continues. Light descends, interacts, is altered, and rises again, each layer adding nuance. The deeper the light travels, the more it is changed. Even the temperature plays a role. Neptune's atmosphere is far colder than Uranus's, and cold temperatures change the way methane ice forms, how hazes clump together, and how particles drift in the air. These subtle differences shape how light moves through the atmosphere. They create regions where blue light deepens into indigo, where sunlight flickers in thin streaks, where the edges of storms glow faintly like buried sapphires. When Neptune's winds carve patterns in the clouds, they reveal shades that shift and darken the way the sea darkens beneath a gathering storm. Yet, despite methane being the key to Neptune's colour, it cannot be the entire story. If methane alone were responsible, Neptune and Uranus would share nearly the same hue they do not. Uranus has a lighter, milder turquoise, peaceful, muted, almost pastel. Neptune, by contrast, carries a blue so deep it seems to hold weight. It has a saturation that suggests something more is at work, something hidden. Planetary scientists have wrestled with this difference for years. Both planets contain similar amounts of methane. Both sit in the cold outer regions of the solar system. Both receive faint sunlight that interacts with their atmospheres in broadly similar ways. And yet the colours diverge dramatically. Neptune's blue is darker, more vivid, more intense. This brings the mystery to one of the most intriguing questions in planetary science. Why is Neptune so much richer in colour than Uranus? The leading idea is the presence of a chromophore, a pigment or substance capable of absorbing certain wavelength of light and shifting the resulting colour toward a more saturated blue. A chromophore does not need to be abundant to have an effect. Even a thin layer of complex hydrocarbons or haze particles can change the balance of wavelengths reflected to space. But the identity of this chromophore remains unknown. Several possibilities have been proposed, from long carbon chains created by ultraviolet radiation to exotic ices forming in Neptune's cold upper clouds. None have yet been confirmed. The evidence is faint, hidden among the layers of a planet nearly impossible to study up close. Some researchers suggest that Neptune's atmosphere may stir itself more vigorously than Uranus's, mixing deeper materials upward into the upper layers. That mixing could bring trace compounds with it, compounds that darken the blue in subtle but noticeable ways. Others think that Neptune's stronger internal heat may help generate more of the particles responsible for deepening the colour. If heat rises from within, carrying chemical byproducts upward, the upper atmosphere could develop a richer, more varied mixture of particles, and therefore a richer shade of blue. The truth may be a combination of these factors, or something entirely different. Until another spacecraft visits Neptune with instruments far more sensitive than those of Voyager 2, the mystery will remain. In the meantime, the unknown pigment stands as a quiet reminder that even familiar chemicals like methane cannot explain everything. Some secrets cling tightly to the cold. The effect of all these processes, the absorption of red light, the scattering of blue, the layering of hazes and clouds, the formation of high-altitude ices, and the possibility of hidden chromophores, produces a world that glows in tones rarely found elsewhere. Neptune's blue is not the bright sky blue of Earth or the gentle turquoise of Uranus. It is deeper, more solemn, more continuous, as though coloured by distance itself. The light seems to seep through the atmosphere rather than sit on top of it, shimmering quietly like a sapphire held beneath icy water. Imagine sunlight filtering down through that atmosphere. It would enter the topmost layers thin and pale, then pass through hazes that soften it into cool strands. Next, it would brush against methane molecules and lose its reds, leaving blues to drift downward. As it reached deeper clouds, it would scatter again, bouncing upward through each layer with a slightly altered hue, until finally it escaped into space and formed the glowing face astronomers see from Earth. Seen from afar, Neptune looks like a world wrapped in stillness. But its colour tells a different story. A story of light travelling immense distances only to be gently reshaped by cold air, tiny particles, and hidden chemistry. A story of wavelengths shifting and scattering until only the shortest, bluest ones survive. And a story of processes so delicate and complex that even now, after decades of study, the full recipe for Neptune's colour remains incomplete. What we do know is that Neptune's blue is not an illusion. It is the product of absorption, scattering, chemistry, temperature, and mystery, all woven together into a single pure tone. And that tone carries the feeling of distance, of a world lit not by brilliance, but by the faint, icy glow of a sun so far away it cannot even cast a true midday. A world where light becomes a whisper, drifting softly through layers of cold blue air. Neptune's atmosphere is a world of layers, each one drifting above the next like sheets of cool, blue silk suspended in the distant dark. From afar it looks smooth, serene, almost simple, but up close the planet reveals a structure woven from different gases, temperatures, and textures, all interacting quietly under the faint glow of a faraway sun. At its foundation, the atmosphere is made mostly of hydrogen and helium, the two lightest elements in the universe swirling together in a cold, weightless sea. Mixed into this blend is methane, which gives Neptune its characteristic colour and shapes the way light moves through the air. But these gases are only the beginning. Higher up, the atmosphere becomes dotted with hazes, fine particles created when sunlight breaks apart, methane molecules, and rearranges them into new, complex forms. The result is a delicate stratification that makes the planet's sky far richer and more layered than it first appears. Peer into the uppermost levels of Neptune's atmosphere, and you would find a thin veil of hydrocarbon hazes suspended in the cold. These hazes act like a soft filter, diffusing sunlight into gentle gradients. Their particles are tiny, almost weightless, drifting with the planet's swift winds the way dust might drift through a quiet room. Because these particles scatter light, they soften Neptune's colours into the deep, velvety blues and faint purples seen by telescopes. In some regions, the hazes grow denser, forming thin sheets that glow faintly when struck by sunlight, as though the entire sky were dusted with powdered ice. Beneath these hazes lie the methane clouds, among the most striking features hidden within Neptune's layers. These clouds are not thick, towering structures like the thunderheads found on Earth. Instead, they form delicate streaks of ice that stretch across the atmosphere like brush strokes on a canvas. Methane condenses in the frigid upper troposphere, turning into tiny crystals that catch and reflect sunlight with a pale, soft shimmer. Seen from afar, these streaks appear as bright patches or thin white lines drifting across the planet's darker blue body. They can change quickly, forming and dissolving as atmospheric currents shift them into warmer or colder regions. In a world as cold as Neptune, these clouds are the quiet breath of the planet, a sign of motion in an environment that would otherwise seem still. Below the methane clouds, Neptune's atmosphere becomes thicker and more complex. Layers of hydrogen sulfide clouds are believed to exist deeper down, forming at pressures far greater than anything experienced near the surface of Earth. These clouds, though invisible from space, add depth and texture to the overall atmospheric structure. They reflect certain wavelengths of light while absorbing others, contributing to the shifting patterns recorded by telescopes. Some layers may form vast sheets, wide enough to span continents, floating in slow currents that move beneath the planet's visible cloud tops. Farther down still, scientists suspect the presence of water-ammonia clouds, dense, powerful systems forming in the extreme cold and pressure of the mid-atmosphere. These deeper clouds are hidden beneath kilometers of gas, unseen but influential. They affect how heat escapes from the planet's interior and help shape the currents that feed into Neptune's legendary storms. They also influence the faint shadows and highlights seen across the cloud tops, even though they remain far below the visible layers. Each layer interacts with sunlight in its own way, creating a kind of vertical tapestry where colour, brightness, and reflection shift depending on the altitude. When the thin light of the distant sun reaches Neptune, it passes first through the upper haze. Much of the red light is absorbed by methane molecules, leaving a surplus of blues. Some of this blue light scatters upward, painting the upper atmosphere in soft azure hues. The rest continues downward, where it encounters the thin methane ice clouds. These clouds reflect part of the remaining light back into space, contributing the bright highlights often seen on the planet's surface. Light that makes it past these upper clouds reaches deeper levels, where it meets thicker layers of gas and more complex hazes. Each time the light descends into a new layer, it is altered. Each time it rises back upward, it carries a trace of the structures it passed through. By the time it escapes into space, it holds the imprint of the entire atmosphere, a combined echo of all the layers working together. Astronomers study these faint signatures using special instruments, teasing apart the different wavelengths to map the hidden architecture of the planet. Through these patterns, they can infer the altitude of clouds, the composition of hazes, and even the speed of winds drifting across the planet's face. Neptune's atmospheric layers are constantly in motion. Fast currents sweep across the upper levels, carrying methane clouds into new shapes. The winds here are the fastest recorded anywhere in the solar system, but despite their incredible speed, the layers shift so smoothly that the atmosphere maintains a sense of graceful calm. The vapors stretch, twist, and merge like threads carried along by an unseen river. When storms form deep below, they push upward, disturbing the upper layers in subtle waves that ripple across the cloud tops. These changes create alternating patterns of brightness and shadow, giving Neptune its dynamic and textured appearance. Even the colour gradients seen across the planet tell a story. The equatorial regions often appear slightly brighter, a sign that the layers there are thinner or that sunlight is interacting differently with local hazes. The mid-latitudes can show deeper shades of blue, suggesting thicker or colder cloud systems. Near the poles, the colours may shift again, influenced by complex circulation patterns that rise and fall like the long breaths of a slow-moving giant. These variations create a world where nothing is uniform, yet everything feels connected, each layer contributing to a grand atmospheric dance that unfolds at a tranquil pace. Imagine floating through Neptune's upper atmosphere, drifting with the winds that wrap around the planet like soft ribbons. The methane ice clouds would pass beneath you like pale, translucent waves. The hazes above would soften the sunlight into gentle gradients, casting the entire sky in deep sapphire tones. The deeper layers, though hidden from direct view, would exert a quiet pressure, shaping the patterns you see like distant hands guiding the flow of air. What appears simple from space becomes a mosaic of moving textures, each one shaped by chemistry, temperature, and the faint whisper of sunlight. This layered atmosphere reveals much about Neptune's nature. It is a cold world, but not a static one. It is distant, but not quiet. Its layers move with a grace that belies the violence of the winds beneath, and its colours, those deep blues, soft streaks, and subtle gradients, are not just properties of light, but reflections of the architecture of the sky itself. Neptune's atmosphere is not one thing but many. A stack of drifting vapours, frozen crystals, and delicate hazes that together create a world both peaceful and profound. Through these layers, sunlight becomes something new. It descends in pale streams, dances among crystals, softens across hazes, and emerges transformed. The atmosphere becomes a lens, a filter, a painter of colour. And the planet beneath becomes a canvas of shifting blues, glowing softly against the darkness of the outer solar system. Neptune is a world of contradictions, and none is more striking than the way its winds behave. In a region of the solar system where sunlight is as faint as a distant memory, where temperatures fall so low that the air itself becomes sluggish, Neptune somehow hosts some of the fastest winds ever recorded. These winds roar across the cloud tops at speeds that break the rules of expectation, racing faster than sound through an atmosphere so cold it should barely stir. It is as if the planet has learned to hide its wildest forces beneath a face of soft blue calm. From afar, Neptune looks serene, a smooth sphere wrapped in quiet colour. But beneath that gentle appearance lies a restless world. Bright storms leap across the surface, dark vortices swirl like enormous shadows, and thin streaks of white clouds whip past at impossible speeds. The contrast is striking. Deep space is silent and still, yet Neptune's atmosphere churns with turbulent energy. One of the most famous features ever seen on Neptune is the Great Dark Spot, a massive storm first photographed by Voyager 2 in 1989. It stretched nearly the size of Earth, rotating like a giant hurricane carved from shadow. Unlike hurricanes on Earth, which rely on warm oceans as fuel, the Great Dark Spot formed in a place where warmth is scarce. The storm's dark centre suggested a deep vortex, spinning so rapidly that clouds were pulled away, revealing darker material from lower layers. Around its edge, bright white clouds formed from methane ice, racing around the vortex like froth around a whirlpool. Near the Great Dark Spot, Voyager 2 also spotted a bright feature nicknamed the Scooter Cloud, This small, fast-moving cloud zipped across Neptune's atmosphere at such incredible speed that it slid ahead of the larger storm systems as though the winds beneath it were carrying it on a swift conveyor belt. The cloud moved so quickly that early observers thought it must be an error or a trick of the camera, but it was real, a plume of methane ice caught in winds that would humble the fiercest jet streams on Earth. Even stranger are the bright white methane ice storms that sometimes appear across Neptune's surface. These storms form when pockets of rising gas cool and condense into crystal clouds, creating towering plumes that glow brightly against the planet's deep blue backdrop. Some of these storms have been observed growing rapidly over just a few hours, then shrinking again as quickly as they appeared. They behave like electrical storms without lightning, boiling upward from the deeper atmosphere before dissolving into drifting vapour. They offer glimpses into the powerful forces shaping the planet from below. What fuels these astonishing winds and storms is a mystery that has intrigued scientists for decades. After all, Neptune receives only a tiny fraction of the sunlight that warms Earth. The faint glow that reaches the planet should not be enough to power winds faster than sound. Yet the atmosphere moves with a vigour that dwarfs anything found closer to the Sun. To understand why, we have to look deeper than the surface, toward the hidden heat rising from within. Neptune emits more than twice the amount of energy it receives from the Sun, a sign that the planet is warmed not from above but from below. Heat left over from the planet's formation, combined with slow gravitational contraction and chemical processes deep inside, rises toward the cloud tops. When this internal warmth encounters the cold outer atmosphere, it sets up powerful circulation patterns that drive winds around the planet. These patterns are strengthened by Neptune's rapid rotation, which creates strong banding in the atmosphere. The combination of rising internal heat and quick spinning creates a playground for extreme winds. Imagine a pot of water on a stove. The bottom is heated, the top is cool, and currents form as the warm water rises and the cool water sinks. Now imagine that pot being spun, and imagine it on a scale far larger than Earth, with temperatures and pressures that twist the currents into fierce spirals. Neptune behaves something like that, only with gases instead of water, and with layers so deep that light may take hours to penetrate them. The result is an atmosphere divided into broad wind belts flowing eastward and westward at different latitudes. Where these belts meet, the wind speeds surge. Some winds blow at more than 1,000 kilometers per hour, fast enough to carry clouds around a planet in just a few hours. The air does not merely drift, it sprints. It tears across the sky with a force that seems impossible for a world bathed in dim twilight. And yet, despite the energy roiling beneath the surface, Neptune still manages to look peaceful from afar. The storms and winds are wrapped in layers of haze and cloud that soften their appearance instead of sharp edges and violent contrasts. The planet presents smooth gradients. The storms blur into the surrounding blue, appearing more like brushstrokes than tempests. The calm veneer of the upper atmosphere hides the raw power surging below, creating a world where appearance and reality drift gently apart. The contrast becomes even more apparent when imagining the silence of space from which Neptune is observed. In the vacuum beyond the atmosphere, nothing stirs. The darkness is absolute. There is no sound, no wind, no motion, only stillness. Yet just underneath that quiet exterior, the planet's air whips around with unimaginable force. Winds that would flatten buildings on Earth slip soundlessly around Neptune's circumference, carving patterns in the clouds without ever making a sound. The contrast is soothing in its own strange way, a reminder that intensity does not always appear loud, and that motion can exist in harmony with calm. If you could drift above Neptune's cloud tops, the experience would feel surreal. The deep blue background would stretch beneath you like an endless ocean, broken only by streaks of white methane ice clouds racing across the surface. These clouds would move with the speed that feels impossible for such a cold, distant world. Some would trace the edges of dark vortices, spiraling around them like snowflakes caught in a whirlwind. Others would skitter across the sky like brushstrokes moving in real time, shaped by currents that never slow. The winds themselves would not be felt directly. In the thin upper atmosphere, they would move around you quietly, carrying methane crystals that shimmer faintly in the dim sunlight. You might watch a storm grow brighter as sunlight catches it at a new angle, then dim again as it drifts behind a band of haze. Everything would move with a rhythm that is both swift and gentle, an elegant contradiction at the edge of the solar system. What makes Neptune's winds even more remarkable is how changeable they are. Some storms appear and disappear within months, while others persist for years, wandering across latitudes before fading from view, the great dark spot observed by Voyager. Two vanished by the time the Hubble Space Telescope looked for it again, replaced by a new dark storm in the northern hemisphere. It is as though Neptune breathes storms into existence, then lets them dissolve in the same quiet way they formed. These rapid changes show that Neptune's atmosphere is active and dynamic, responding to internal heat and rotation in complex ways. The storms may rise from deep below, where warmth churns the gases, then fall back as the upper layers cool them. Each one tells a small part of the larger story of how the planet redistributes energy from its core to its surface. Watching Neptune is like watching weather on fast forward, sped up not because time moves differently, but because the planet's internal forces are always shifting. For all its contradictions, Neptune's atmosphere remains one of the most mesmerizing environments in the solar system. It is a world where sunlight is weak but winds are strong, where cold air moves with fierce energy, and where storms bloom in silence beneath a serene sapphire sky. It offers a gentle reminder that even in the most distant corners of the cosmos, motion and mystery coexist. Quiet on the outside, powerful on the inside, always drifting, always changing, always waiting to be understood. Neptune lives far from the sun, drifting in a realm where light grows thin and warmth feels almost impossible. Yet beneath its cold blue exterior, the planet carries a secret. It emits more than twice as much heat as it receives from the distant sunlight. In a place where the sun appears no brighter than a star, Neptune somehow shines from within. That quiet internal warmth shapes nearly everything the planet does, from the speed of its winds to the rise of its storms, as though a faint inner fire were breathing life into an otherwise frozen world. The idea seems almost contradictory. Neptune is the fourth largest planet, a giant ball of gas and ice wrapped in temperatures so low that methane condenses into crystals and sunlight fades into silver. Nothing about its environment suggests heat, and yet measurements taken by spacecraft and telescopes have shown that Neptune glows in infrared wavelengths, releasing energy that cannot be explained by the weak sunlight alone. This heat must come from the inside, rising slowly through the atmosphere before leaking out into space. The warmth is not dramatic. It is not enough to melt ice or create blazing hotspots, but it is steady, persistent. A quiet heartbeat inside a distant world, Scientists have proposed several explanations for this subtle glow. One of the simplest is leftover heat from Neptune's birth. When planets first form, they collect enormous amounts of energy as gas and dust fall inward, compressing under gravity. That energy becomes trapped deep inside, slowly radiating outward over billions of years. Most planets eventually cool as they age, but Neptune may still be holding on to a portion of that ancient warmth. It is as though the planet remembers the earliest moments of the solar system, keeping a soft ember glowing beneath its stormy clouds. Another possibility lies in the way Neptune's interior is structured. The planet is made of hydrogen, helium, and volatile compounds like water, ammonia, and methane, all layered under crushing pressure. As heavier materials gradually settle toward the center, they release gravitational energy, much like a stone dropping deeper into a pond transfers energy into the water around it. This slow sinking could produce heat that rises toward the atmosphere. It would be an ongoing process, invisible but persistent, adding energy to the planet's circulation patterns over unimaginably long periods of time. There may also be chemical interactions deep within Neptune that release heat. Under extreme pressures and temperatures, molecules behave differently than they do on Earth water, and ammonia can form exotic crystalline structures. Methane can break apart and reform into new compounds. These transformations may release small amounts of energy, contributing to Neptune's internal warmth. None of these processes would produce dramatic explosions or fiery cores. Instead, they behave more like slow, quiet reactions happening in the depths of a planet where light never reaches. Whatever the source, Neptune's internal heat has profound effects on its atmosphere. While the sunlight that reaches Neptune is faint, the heat rising from below is surprisingly strong. It warms the lower layers, creating gentle updrafts that travel upward like warm breath rising through cold air. When that warmth meets the frigid outer atmosphere, it sets off powerful circulation patterns, cells of rising and sinking gas that transport energy across the planet. These circulations help generate the extreme winds that sweep across Neptune at incredible speeds. They also feed the storms that form and dissolve across its cloud tops, giving the planet a restless, dynamic character. Imagine a lantern glowing under layers of cloth. The outer fabric may feel cool to the touch, but the warmth from within creates subtle currents of air, shifting the folds and stirring the patterns on the surface. Neptune behaves much the same way. Its outer layers are cold enough to freeze methane, yet beneath that surface the heat continually pushes upward, shaping the movements of the clouds. When a deep pocket of warmth rises quickly, it can create a bright storm, sending methane crystals swirling upward in a burst of white. When the internal heat shifts direction or weakens, those storms fade again, dissolving back into the blue haze around them. This internal motion explains why Neptune's atmosphere is far more active than Uranus's. Despite both planets receiving nearly the same amount of sunlight, Uranus emits only a tiny bit more heat than it receives, and as a result its atmosphere is calmer, more uniform, quieter. Neptune, with its extra stores of warmth, acts like a kettle kept on low heat. It never boils, but it always simmers. Patterns swirl, winds accelerate, clouds form and vanish like mist brushed across a window. The faint heat keeps the atmosphere alive, stirring it gently but continuously. Some researchers believe that this internal heat may even help explain why Neptune's winds break records. When heat escapes unevenly from the planet's interior, it can create powerful differences in pressure. Those differences stretch across huge distances, and because Neptune rotates quickly, the rising and falling air becomes twisted into long, fast-moving jets. These jets encircle the planet, growing stronger as they feed on the temperature contrasts created by the heat. It is a delicate dance between warmth and cold, motion and stillness, played out on a stage where sunlight plays only a minor role. The presence of this internal glow also raises questions about the planet's evolution. If Neptune is still shedding heat after billions of years, it may have cooled more slowly than scientists expected. This could mean that its interior is layered in ways not yet understood, or that heat becomes trapped in deep pockets before escaping upward. It suggests a complex world beneath the clouds, one shaped by processes that are difficult to imagine from the surface of Earth. The outer shell of Neptune may be cold enough to freeze breath instantly, but beneath that shell lies a history written in warmth. There is something soothing about imagining a world warmed from within. Neptune does not shine loudly. It does not blaze with the intensity of a star or burn with molten rock like Earth's core. Instead, it carries a hidden softness, a glow that seeps upward through its layers, gentle and persistent. It keeps the planet breathing, keeps the storms alive, keeps the winds turning endlessly around the globe. It is a reminder that warmth does not always announce itself with brightness. Sometimes it moves quietly, shaping the world in ways that can only be seen through the movement of clouds and the whisper of storms. Picture that inner glow rising toward the surface. It would travel through layers of exotic ice, through liquids that behave like solids, and solids that behave like liquids, through gases so cold they shimmer. By the time it reaches the cloud tops, the warmth is faint, like the last ember of a dying fire. But even that faintness is enough. It spreads across the atmosphere, stirring it with gentle fingers, encouraging winds and wakes and currents. Then it slips out into space, adding a thin veil of infrared light to the planet's silent orbit. Neptune's warmth is not a flame, it is not a blaze. It is more like the lingering heat of a memory, leftover energy from the planet's first days, transformed by time and pressure into the quiet glow that sustains its storms. Beneath its cold blue shell, Neptune carries its history like a hidden lantern, casting a soft light that guides the motion of its winds. And though the source of that warmth remains partly mysterious, its effects can be seen every time a storm blossoms across the planet's face or a band of clouds shifts quietly in the dark. In the end, Neptune's glow is a reminder that distance does not always mean stillness. Even in the furthest reaches of sunlight, a world can keep a fire burning deep within, shaping itself with warmth that never quite fades. Deep beneath Neptune's clouds lies a realm unlike anything on Earth, a mantle made not of rock or molten stone but of water, ammonia, and methane compressed into forms that defy ordinary imagination. In this hidden region, where pressures climb to millions of times those at sea level, and temperatures rise far beyond anything felt on the surface, the familiar rules governing matter begin to loosen. Liquids behave like solids. Solids behave like liquids. Molecules drift and shudder in states that do not exist anywhere on our planet. It is a world where chemistry stretches itself into new shapes, shaped by forces so extreme that the boundary between materials becomes a shifting, fluid thing. In everyday life, water freezes into ice or flows as liquid. Methane exists as a gas or, when chilled, condenses into a light liquid. Ammonia, too, transitions between solid and liquid depending on pressure and temperature. but these simple categories dissolve in Neptune's mantle. Water is pushed into exotic forms by pressures so great that the molecules are forced into unnatural arrangements. Methane becomes unstable, breaking apart into carbon and hydrogen under the immense weight above it. Ammonia, trapped in the same deep regions, rearranges its atoms in combinations rarely seen. The mantle becomes a vast interior ocean of substances that behave in unfamiliar ways, swirling in silence beneath the planet's outer layers. At moderate depths, the mixture of water, ammonia, and methane exists in a phase sometimes described as a dense, hot, slushy fluid, far from solid, yet far from liquid. Temperatures in these regions soar to thousands of degrees, hot enough to glow if the material were exposed to space, but the crushing pressure prevents it from evaporating or boiling. Instead, the mixture flows slowly, heavy and luminous, as currents move through it with the weight of something neither fully fluid nor fully frozen. Imagine an ocean sealed beneath a shell, where every wave is squeezed by gravity and shaped by heat, moving with a muted, deliberate grace. Deeper still, the conditions become even more extreme, and water begins to transform into something even stranger. Hydrogen atoms, usually bound tightly within the water molecule, begin to drift away under intense pressure. Oxygen atoms remain locked into a rigid lattice, forming a structure that resembles a solid crystal. But within that structure, hydrogen atoms move freely, sliding and flowing through the lattice like a liquid threaded through stone. This is supersonic water, a phase neither ice nor liquid, but something in between, a substance that behaves like a glowing, conductive hybrid. Supersonic water is one of the most exotic forms of matter theorized and studied in planetary interiors. In laboratory experiments using powerful lasers and diamond anvils, scientists have recreated tiny flashes of this state, enough to measure how it behaves. What they found is astonishing. The oxygen atoms stay nearly fixed, forming a stable grid, while the hydrogen atoms migrate chaotically through the lattice. The material conducts electricity, glows under extreme heat, and behaves like a liquid that cannot flow, trapped and yet active. It is the kind of matter that seems more at home in science fiction than in the quiet depths of a real planet, and yet on Neptune it may be abundant, forming vast layers within the mantle. This supersonic water likely plays a role in shaping Neptune's magnetic field. On Earth, the magnetic field is generated by molten iron flowing in the outer core, but Neptune does not have such a metallic core. Instead, the mantle's exotic conductive materials may create electrical currents as hydrogen ions drift through the supersonic lattice. These currents could produce the planet's tilted, offset magnetic field, a field so unusual that it suggests layers of dynamo activity far above the core. The mantle, in other words, is not just a passive layer. It is active, energetic, and essential to the planet's behavior. Returning to the strange chemistry in the mantle, methane under these pressures can break apart into hydrogen and carbon. The carbon may then compress into diamond crystals, which could sink deeper into the planet like glittering rain. The hydrogen rises towards shallower layers, altering the composition of the region above. Ammonia molecules too may reorganize into structures not found naturally on Earth, forming unusual compounds under pressure that dissolve into the mantle's fluid motions. These changes happen slowly and silently, but their collective effects shape the entire interior of the planet. Imagine descending into this mantle. At first, the layers would seem thick and heavy, moving with the sluggish motion of a world trapped between liquid and solid. Deeper down, The material would glow with internal heat, illuminated from within like glass warmed in a fire. The deeper you drift, the stranger the environment becomes. Matter stiffens but still flows. Elements combine in patterns that only intense pressure allows. A vast, dark ocean stretches downward, one that has no waves, no surface, no floor, only gradients of pressure and temperature that transform everything they touch. The silence of this interior world would be profound. There are no cracks or bubbles as on Earth, no shifting crust, no magma chambers bursting into eruptions. Instead, Neptune's mantle evolves with the quiet patience of a planet too distant and too cold for noise. Even the currents that drift through it move slowly, driven by heat rising from the core and the slow descent of materials rearranged by pressure. Each motion is deliberate, as though the whole interior were caught in a long, slow dream. The boundaries between layers blur. At one depth, the mixture may behave like a superheated fluid. A little deeper, it might become more rigid, resisting flow. Deeper still, superonic phases begin to dominate, glowing faintly as ions slip through the lattice. The deeper you go, the more the environment becomes a world all its own, governed not by the familiar phases of matter, but by the intense rules of the giant planets. This exotic mantle helps explain why Neptune behaves the way it does. The planet's internal heat, which sustains its storms and drives its fast winds, rises through this swirling interior. The movement of ions within supersonic water contributes to the magnetic field, twisting and shifting its shape. The chemistry within the mantle determines the composition of gases that eventually reach the atmosphere. Every change within this deep interior sends ripples upward, influencing the cloud tops and storms far above. Despite being inaccessible to direct observation, this mantle remains one of the most fascinating places in the solar system. It shows that water is not always gentle, that methane is not always a simple gas, and that ammonia can become part of something far more complex. Under enough pressure and heat, these substances we know transform into states that feel almost alive, changing shape, releasing energy, guiding currents, and carrying the memory of a planet's formation. There is a calm beauty in imagining these silent oceans of unfamiliar matter. They stretch outward from the core, drifting, glowing, compressing. They move with slow grace, stirred by ancient forces. And though hidden beneath thousands of kilometers of atmosphere, they help define the planet as a whole. Neptune is not just a blue sphere in the cold. It is a world where matter rewrites itself in the darkness, forming layers rich with secrets, each one whispering stories of pressure, heat, and transformation. To understand Neptune fully, one must picture this mantle not as a barrier, but as a vast, dynamic sea. A sea that hums softly with heat. A sea made of exotic materials. A sea whose surface we will never touch, but whose influence reaches all the way to the clouds we see. In that deep and silent ocean, the planet keeps its most remarkable mysteries, held beneath a shell of cold blue, waiting in the dark. Deep beneath Neptune's serene blue clouds, far below the storms and winds that sweep across its surface, there may be rain unlike anything found on Earth. Not rain made of water, nor of methane, nor of ammonia, but rain made of diamonds, crystals forming in the warm, crushing dark of the planet's vast interior. It sounds like a dream, a story whispered from the edge of imagination, yet the science behind it is built on pressures and temperatures that reshape molecules into entirely new forms. In the deep mantle where ordinary rules dissolve, carbon may be pressed so tightly that it crystallizes into diamonds, which then sink slowly toward the core like shimmering stones in an endless sea. To understand how such rain might form, it helps to picture the composition of Neptune. The planet is rich in methane, a molecule made of one carbon atom bonded to 4 hydrogen atoms. Closer to the surface, methane drifts as a gas, contributing to Neptune's blue color. But as you descend deeper into the planet, toward layers where pressures rise to millions of times those at Earth's surface, methane becomes unstable. The enormous weight squeezing down on each molecule forces the atoms into new arrangements. The carbon, once comfortable in its bonds, begins to separate from the hydrogen, like a structure gently breaking apart under strain. Once freed, the carbon atoms find themselves in a world where the pressure is unimaginably high. Under such conditions, carbon cannot remain in its normal forms. Instead, it begins to pack itself into dense crystalline lattices, the kind seen in diamonds. These diamonds may begin as tiny grains no larger than dust motes, forming spontaneously throughout the mantle, but as they drift downward, they may compress further, gathering into larger crystals as more carbon accumulates. Over time, entire regions of the mantle could sparkle with forming diamonds, each piece responding to the intense forces that sculpt them. Scientists studying this possibility cannot travel to Neptune's interior, but they can recreate some of the conditions in laboratories on Earth using devices known as diamond anvil cells, tools that can squeeze materials between 2 small diamond tips. They compress methane and similar compounds to pressures found on giant planets. Powerful lasers heat the samples, creating a brief but intense replica of Neptune's mantle environment. In some of these experiments, after the high pressure and heat are applied, carbon structures form within the sample. These structures are microscopic diamonds. The discovery was remarkable. It showed that the concept of diamond rain was not just speculation, but had a basis in physical reality. Researchers watched the carbon atoms shift, reorganize and crystallize under conditions they believed mirrored the deep interior of Neptune. It suggested that in the giant planets, this transformation may not only be possible, it may be common. The process begins with the breaking of methane. Under milder conditions, methane is stable, its carbon held tightly in a cage of hydrogen atoms. But when the molecules are crushed under immense force, the bonds stretch beyond their limit. Hydrogen atoms slip away, freed into the surrounding fluid, while carbon atoms are left behind. With the hydrogen gone, the carbon rearranges itself into solid structures. The lattice remains stable even as temperatures soar. What emerges is a new crystal, shaped not by cooling, but by compression. If we imagine descending into Neptune, we might picture the outer layers as drifting clouds, then thicker fumes, then a phase where methane becomes dense and warm. As we go deeper still, the environment becomes a blend of exotic liquids and supersonic phases, glowing faintly with internal heat. Eventually, in the darkness where chemical bonds stretch and break, carbon begins its quiet transformation. The crystals form without ceremony, appearing in the dense fluid like sparks frozen in motion. Once formed, the diamonds begin to fall. Gravity pulls them toward the planet's core, a region where pressures grow higher still. The diamonds drift downward through the mantle, pulled by weight but slowed by the thick, heavy fluid surrounding them. It is not a rain as we know it. There is no pattering, no droplets, no familiar rhythm. Instead, it would be a slow, silent descent of glittering particles, dropping through layers of unfamiliar matter. Some crystals may dissolve again as they enter hotter regions. Others may survive and continue falling, joining larger structures or settling into a layer where their motion slows. The descent may create a region deep inside Neptune where diamonds accumulate, forming a vast crystalline interior. Some scientists speculate that layers or clusters of diamond could exist there, compressed into shapes and sizes beyond anything found naturally on Earth. These diamonds would not sparkle. They would sit in darkness, warmed by the planet's interior heat, existing under pressures strong enough to change their properties. Still, the idea of such a region is a reminder of how differently matter behaves under conditions far beyond our everyday experience. The hydrogen left behind after methane breaks apart would rise upward, adding to the composition of layers above. In this way, the separation of methane into carbon and hydrogen may influence the chemistry of the entire mantle, shaping how the planet stores and transports heat. The transformation of carbon into diamond is not just a curiosity, it is part of the dynamic interior processes that govern Neptune's behaviour. The dreamlike imagery comes naturally, shimmering crystals drifting downward in warm darkness, forming in silence as invisible forces guide them. It is easy to imagine the deep interior lit not by light, but by the chemistry of the planet itself, each crystal a silent witness to the immense forces that created it. The scene feels distant, almost mythical, yet grounded in measurements and experiments that point toward its truth. This diamond rain may also help explain why Neptune emits so much internal heat. As diamonds form and sink, they release gravitational energy, small amounts from each particle, but immense when multiplied across billions of crystals forming over millions of years. As they drop deeper, they compress materials below them, generating additional warmth. In this view, diamond rain is not merely a beautiful idea, it is part of the planet's internal engine. It may seem strange to think of a planet filled with exotic matter and shimmering precipitation, but Neptune's interior is governed by rules written in pressure and heat. The planet holds on to its secrets behind layers of methane, water, and ammonia, each layer hiding another beneath it. Yet through experiments and careful modelling, scientists glimpse a world where diamonds fall like snow and where atmospheric chemistry writes stories in the dark. In the distant reaches of the solar system, Neptune reminds us that beauty does not always need light to exist. Deep inside its mantle, where sunlight never reaches, diamonds may form and drift, shaped by forces older than any storm or cloud. They are born in silence, falling through a warm ocean of unfamiliar elements, glowing only in the imagination, yet grounded in physics. It is a quiet wonder, hidden beneath a cold blue shell, waiting patiently for understanding to catch up. Far out in the quiet reaches of the solar system, Neptune carries a magnetic field unlike anything close to home. Instead of being neatly aligned with its rotation, or centered within the planet, Neptune's magnetic field is dramatically tilted and strangely shifted, as though the entire structure were drifting through the planet rather than anchored at its core. While Earth's magnetic field emerges from deep within a molten, rotating iron core spreading outward in a predictable pattern, Neptune seems to arise from somewhere in its mantle, off-center, angled and weaving through the atmosphere in a way that defies simple symmetry. It is as if a bundle of invisible threads has been wrapped around the planet at a crooked angle, twisting and bending in ways that seem both chaotic and strangely graceful. On Earth, the magnetic poles sit roughly opposite each other, close to the axis around which the planet spins. This alignment creates a magnetic field that is relatively stable, forming a familiar doorbell shape. A north pole, a south pole, and lines of force looping outward in a smooth, symmetrical pattern. Compasses work because of this neat alignment. Auroras occur near the poles because solar particles spiral down along predictable magnetic pathways. Everything feels orderly, as though the magnetic field follows a well-practiced routine. Neptune tells a different story. Its magnetic pole is neither near the geographic pole nor centered within the planet. Instead, the magnetic axis is tilted by almost half a right angle from the rotation axis, creating a field that seems to wobble, twist, and drift as the planet spins. Even more curiously, the magnetic field is offset from the planet's center by a substantial fraction of the planet's radius. Imagine holding a bar magnet not in the middle of a globe but closer to the surface, and then tilting it sharply. The result would be a field that flares out unevenly, stronger in some regions, weaker in others, and constantly shifting as the world turns. This off-center structure means that Neptune's magnetic environment is constantly changing. As the planet rotates, the tilted magnetic field sweeps around like a lighthouse beam, creating zones where the magnetic influence intensifies, and others where it fades. Charge particles caught in this shifting field dance in irregular patterns, spiraling in ways that depend on the planet's rotation and the geometry of the field at any given moment. It is a magnetic ballet that never repeats the same steps twice. One of the most striking consequences of Neptune's unusual magnetic field is the nature of its auroras. On Earth, auroras cluster around the poles, forming circular rings of shimmering light. They appear where the magnetic field guides solar particles downward into the atmosphere. But on Neptune, the auroras do not sit neatly near the poles. They can appear at unexpected latitudes, drifting across regions where the magnetic field happens to funnel charged particles. Some auroras may shine far from where intuition suggests, glowing faintly under the dim light of the distant sun. Because the planet's magnetic field is so offset and so sharply tilted, these auroras can behave in ways that seem unpredictable, appearing not as steady halos but as irregular glimmers stitched into the planet's thin upper atmosphere. The origin of this magnetic peculiarity lies deep inside Neptune itself. Unlike Earth, Neptune does not have a large molten iron core acting as a dynamo. Instead, the magnetic field likely arises in a shell of electrically conductive fluid in the mantle, possibly a layer of superionic water, ionic fluid made of water, ammonia and methane. In this environment, hydrogen ions move freely through a rigid oxygen lattice or complex chemical mixture, creating the currents needed to generate a magnetic field. But because this layer is not centered or uniform, the field produced is skewed, twisted, and offset. Imagine trying to weave a basket while spinning it at the same time and sliding the weaving point farther off-center. The resulting pattern would be intricate, asymmetrical, and full of unexpected curves. Neptune's magnetic field is woven in a similarly off-balance way, creating a tapestry of invisible lines looping around the planet in shapes that seem whimsical compared to Earth's ordered geometry. These threads of magnetism extend far into space, forming a magnetosphere that fluctuates with the flow of solar wind. At Neptune's distance, the solar wind is weaker and thinner, but still enough to tug at the planet's field, reshaping it and sometimes compressing it on one side, while allowing it to stretch into a long tail on the other. Because the magnetic field is tilted, the magnetosphere flaps and twists with each rotation. If someone were watching it from a distance, It would resemble a giant shimmering bubble being rhythmically squeezed and stretched, gently rippling like a sheet of silk caught in a slow breeze. The magnetic field also affects how particles move within Neptune's atmosphere. Charged particles trapped in the field can follow looping paths, spiraling through regions where the magnetic intensity rises or dips. These movements can generate faint glows, radio emissions, and subtle changes in atmospheric chemistry. Earth experiences similar effects, but Neptune's off-center field makes the patterns more complicated, like tracing lines in a sculpture that shifts shape as you walk around it. For spacecraft that have flown near Neptune, the magnetic field offered both fascination and challenge. Voyager 2, the only mission to visit Neptune up close, detected the strange tilt and offset during its flyby in 1989. Instruments aboard the spacecraft recorded rapid changes in magnetic orientation as the planet rotated, confirming that the field was not only unusual but actively dynamic. The discovery suggested that Neptune's interior was far more complex and fluid than scientists had imagined. A deep, restless ocean of conductive materials generating a field that pulsed with each turn of the planet. Despite its strangeness, Neptune's magnetic field fits the essence of the planet itself. Neptune is a world of contrasts, calm blue on the outside, turbulent within, faint sunlight above, rising heat below, serene colours masking fierce winds, and a distant orbit wrapped around a heart that still holds warmth. Its magnetic field matches this duality, peaceful from afar yet full of hidden complexity, twisting and offset like a thread pulled gently out of place but still part of the larger fabric. If someone could visualize Neptune's magnetic field directly, they might imagine luminous ribbons spiraling around the planet. Some would twist close to the surface, curling like delicate fibers. Others would stretch far into space, forming arcs that bend with the flow of the solar wind. As the planet turns, these threads would shift, braid, separate and rejoin, creating a pattern that never stops moving. In the quiet of deep space, this invisible weaving would remain unseen, yet it would shape everything from auroras to atmospheric currents. What makes Neptune's magnetic field so captivating is that it refuses to sit neatly within the categories we understand. It is neither symmetrical nor stable in the way Earth's is, and yet it is not chaotic in the sense of randomness. Instead, it follows rules written by pressures, temperatures and motions deep within the planet, rules that produce beauty through imbalance. The field's tilt and offset become part of Neptune's identity, reminding us that worlds far from the Sun follow their own logic. In the end, the magnetic field of Neptune is an elegant puzzle composed of invisible forces, a network of lines twisting in calm, graceful arcs around a planet wrapped in blue. It glows softly with auroras where no auroras should be. It shifts and leans, much like a lantern carried slightly off-center. And beneath it all, hidden in the mantle's exotic materials, the currents of the planet flow, weaving a field that circles Neptune with quiet persistence. Always moving, always changing, always keeping its secrets slightly out of reach. Neptune's rings are some of the most delicate structures in the solar system, thin ribbons of dust and dark material drifting quietly around a distant blue world. Unlike the bright, icy rings of Saturn, Neptune's are faint, subtle, and easy to miss, even when telescopes know exactly where to look. They circle the planet like whispers, present, but only barely visible, as though they are shy about reflecting the dim light that reaches them. These rings do not gleam or shine. Instead, they resemble dark traces etched lightly across the sky, composed of material so fine and so shadowed that even powerful observatories struggle to see them. Their faintness begins with what they are made of. The particles in Neptune's rings are coated in dark organic material, likely formed when sunlight breaks down methane and other molecules in the planet's atmosphere. These carbon-rich compounds settle on dust grains, soot-like and light-absorbing, giving the rings a colour that blends into the blackness of space. The particles are tiny, often no more than fragments of ice or rock coated with this dark material. Because they reflect only a small fraction of the sunlight that reaches Neptune, the rings remain nearly invisible from Earth, glowing only faintly in scattered light. Even large telescopes see only hints. From Earth's surface, Neptune itself appears as a small disk, far away and blurred by our atmosphere. The rings, so thin and dark, become nearly impossible to detect. Only when Voyager 2 approached Neptune in 1989 did humanity gain a clear first look. The spacecraft's cameras, positioned above the planet's glare and free from Earth's atmospheric distortion, revealed arcs of dust, thin, curved shapes shimmering faintly against the soft blue backdrop. These arcs are among the most peculiar features of Neptune's ring system. Unlike the continuous rings around Saturn, Jupiter, and Uranus, Neptune's rings are incomplete in places in several sections. The material clumps together into bright arcs, short, dense segments where dust and ice gather more closely than anywhere else. These arcs have names like Liberté, Égalité, and Fraternité, chosen to evoke connection and unity, though their behaviour is anything but simple. Each arc is a region where ring particles cluster tightly, held in place by forces that are still not fully understood. Between these arcs, the rings become sparse, thin, almost non-existent. The mystery deepens when considering how unstable such arcs should be. In a typical ring, particles spread out over time, smoothed by gravity and collisions until the material forms a continuous band. But on Neptune, something keeps the arcs gathered, preventing them from dispersing. It is as though invisible hands reach out in specific places, gathering dust grains and holding them together in clusters. These arcs persist for years, shifting slowly but never smoothing out completely. The leading explanation involves the gravitational influence of Neptune's shepherd moons. These small moons orbit close to the rings, tugging on the particles with just enough force to herd them into place. Galatea, in particular, is believed to play a vital role. It circles the planet just inside the Adam's ring, one of Neptune's outermost rings, and its gravitational pull nudges the ring particles in a repeating pattern. Like a shepherd guiding a flock, the moon's influence encourages the dust to gather, helping maintain the arcs against the natural tendency to spread. The effect is subtle, but over time it becomes powerful, corralling the particles into bright clusters that drift along the ring's path. Even with this explanation, the arcs remain puzzling. Shepherding can account for some of their stability, but not all. Something else may be working with the moon's gravity, perhaps resonances between particles, or tiny variations in Neptune's gravitational field, or processes involving collisions and rebounds unique to the dark carbon-rich dust. Whatever the cause, the result is a set of rings that feels almost handcrafted, each arc a delicate ornament drifting around a vast planet. Imagine floating far above Neptune and looking down on the rings. They would appear as thin, dark strokes curling around the blue sphere, more like shadows than solid structures. The arcs would glint faintly when they caught the sun at the right angle, small sparks against a backdrop of deep sapphire. The rings would not overwhelm or dazzle, they would invite quiet attention. Their beauty comes not from brightness, but from subtlety, the kind that rewards patience, revealing itself slowly. The rings are not uniform either. Some are broader, others narrow. Some contain more dust, while others consist mainly of icy fragments. Each ring tells a story about the planet's past, about collisions, captured objects, and the gradual grinding of material into fine particles. The darker material suggests that the rings may not be ancient. Dark dust tends to absorb sunlight and break apart over time, meaning the rings might be young, constantly replenished by the slow erosion of shepherd moons, or by material thrown from their surfaces when struck by micrometeorites. The interplay between the rings and the moons is delicate. As the moons move, they tug gently on the rings. As the rings shift, they tug back. The result is a dance of gravitational influence playing out over thousands of kilometers. These forces shape the arcs, define the ring's edges, and keep the entire structure bound together despite the planet's strong winds and dynamic atmosphere. What makes Neptune's rings particularly captivating is how they complement the planet's personality. Neptune is a world of subtlety, its storms hidden beneath layers, its heat rising quietly from within, its magnetic field leaning off-center. The rings match this quiet complexity. They do not shout their presence across the solar system the way Saturn's do instead. They trace the planet with delicate, understated lines, barely visible yet deeply significant in the story of Neptune's structure and history. In the dim light reaching Neptune, the rings likely appear ethereal. If someone were floating nearby, the sunlight would filter through the dust like faint smoke. The arcs would shimmer softly, their particles glinting like a handful of dark sand scattered through starlight. The rings might curve across the sky like the thinnest of halos, fragile and transient, illuminated just enough to remind you they exist, but never bright enough to reveal themselves fully. Viewed from this close, the shepherd moons would drift along the rings, tiny by comparison to the giant planet behind them. Their gravity would nudge the particles into place, guiding the arcs with movements so small they would be impossible to perceive in real time. Yet over years and decades, the moons sculpt the rings with quiet persistence, shaping a structure that endures despite the forces working to pull it apart. Neptune's rings stand as a testament to subtle beauty. They show that not everything in the universe announces itself loudly. Some wonders are quiet, hiding in the shadows, waiting for the right vantage point to reveal themselves. The faint, dusty bands around Neptune are not showpieces. They are gentle strokes of darkness that circle a world of deep blue, adding texture to the silence of the outer solar system. Their arcs and curves remind us that even in places where sunlight fades and temperatures drop to extremes, patterns still form. Guided by gravity and shaped by time, Neptune's rings are thin ribbons of softly drifting matter, circling a distant giant in graceful loops, barely visible yet profoundly meaningful, threads of darkness woven around a world of shifting blue. Triton moves through Neptune's darkness in a way no moon should. Instead of orbiting in the same direction that Neptune spins, it travels backward, circling the planet in a slow, retrograde sweep that defies the rhythm of the rest of the system. This lone reversal is more than a curiosity. It is a clue, a sign that Triton was not born in Neptune's embrace. Its backward orbit suggests a dramatic past, one that likely began far beyond Neptune in the icy reaches of the Kuiper Belt. Long ago, Triton may have drifted through that remote region as a dwarf planet, orbiting the Sun in solitude before Neptune's gravity captured it. That capture would have been violent and transformative, reshaping both Triton's orbit and its interior. Since then, the Moon has been carried along like a reluctant companion, held tightly by Neptune but forever marked by its origins in the deeper dark. Because Triton came from the Kuiper Belt, it carries the texture of that ancient frontier. Its surface shines with ices that tell of frigid temperatures and quiet, distant origins. Nitrogen, methane, and carbon monoxide frost its plains, forming pale, smooth expanses that stretch for hundreds of kilometers. Triton's crust reflects sunlight in muted tones, giving the Moon an otherworldly glow that feels more dreamlike than real. But beneath that quiet beauty lies a world in motion, one that refuses to behave like a frozen relic. Voyager 2 revealed the first hints of Triton's restless nature in 1989. As the spacecraft approached the Moon, it photographed something extraordinary. Dark streaks running across the icy surface, as though someone had drawn sharp lines with ink. These streaks were not shadows or geological scars. They were trails left behind by nitrogen geysers erupting from below, sending plumes of gas and dark particles into the thin atmosphere. The geysers rose several kilometers before the winds carried the particles sideways, raining them down in long, straight lines that marked the direction of the breeze. It was the first time active geysers had ever been seen on a world beyond Earth, and they revealed Triton as a place where cold does not mean stillness. These eruptions happen because sunlight, faint as it is at Neptune's distance, warms Triton's surface just enough to trigger change. Beneath the thin layer of frost, nitrogen ice can trap heat. When that heat builds to a critical point, the nitrogen transforms rapidly into gas, pushing upward until it breaks through the surface. The result is a jet, quiet, powerful, and almost invisible except for the dust it carries. These geysers sculpt Triton's landscape, smoothing plains and leaving trails that stretch straight and crisp across the Moon's bright surface. They are signs of an active world shaped by cycles of freezing and thawing, a place where geology dances slowly beneath the cold. The atmosphere that carries those particles is astonishingly thin, almost weightless compared to Earth's. It is made mostly of nitrogen, with traces of methane, and behaves more like a delicate veil than a substantial layer of air. If you stood on Triton, the skies would appear nearly black even in daylight. Yet the atmosphere is thick enough to create winds, faint currents that carry particles long distances, shaping the patterns left by the geysers. These winds glide softly across the surface, picking up dust and laying it down again in strokes of grey and black. Despite its thinness, the atmosphere breathes with Triton's cycles of warming and cooling, swelling slightly during the long summer and contracting during the long winter. Triton's icy plains are some of the youngest in the solar system. They are smooth, bright, and nearly unscarred by craters, a sign that the surface has been renewed repeatedly. In some areas, the ice stretches out in sheets broken only by ridges and ripples, patterns created by the slow shifting of the crust. In others, strange textures emerge, patches that resemble frozen lakes or fields of fractured glass. These features hint that Triton's interior may be warm enough to reshape the surface from below, pushing up fresh layers of ice or causing older layers to collapse and refreeze. The Moon's exterior may seem frozen in time, but its surface tells of change and renewal. Beneath these icy plains, scientists suspect a hidden ocean might exist. The idea comes from multiple clues. Triton's surface shows signs of geological activity, too much for a world expected to be dormant. The moon's density suggests a mixture of rock and ice, a combination that could trap heat inside. And if tidal forces still need Triton's interior, even gently, they could maintain enough warmth to keep an ocean from freezing solid. This ocean, if it exists, would be sealed beneath a shell of nitrogen and water ice, locked away in silent dark. It might contain ammonia as well, which lowers the freezing point of water and makes liquid more stable. Triton could therefore hide as deep, salty, ammonia-rich ocean beneath its crust, a world within a world, preserved beneath the cold. If such an ocean exists, it would make Triton one of the most intriguing moons in the solar system. Oceans beneath ice have become some of the most compelling places to study in the search for life. Although Triton lies far farther from the Sun than Europa or Enceladus, the same principles apply. Where there is liquid water, energy, and interesting chemistry, the possibility of something stirring cannot be dismissed. Even if the ocean is lifeless, its presence would transform our understanding of Triton, showing that even in the distant dark, warmth and motion persist. Triton also has mountains and cliffs carved from ice rather than rock. Some ridges rise like frozen waves, some plains resemble sheets of wind-polished glass. Others show signs of being resurfaced by cryovolcanism, volcanoes that erupt freezing fluids instead of molten rock. On a world where nitrogen geysers pierce the surface, the idea of icy volcanoes becomes almost expected. These cryovolcanoes may release slushy mixtures of water, ammonia, and other volatiles, which then refreeze into smooth plains. The landscape becomes a record of cold eruptions, preserved in patterns and textures that tell stories of deep interior motion. Triton's retrograde orbit adds another layer of intrigue. A moon captured from the Kuiper belt would have entered Neptune's gravitational field with tremendous energy. To settle into a stable orbit, Triton must have lost that energy somehow, perhaps through interactions with another moon, or through tidal forces that heated and reshaped its interior. This capture likely disrupted Neptune's original moon system, scattering or destroying earlier companions. Triton's presence may be the reason Neptune's largest moons are relatively small. The moon that once wandered the Kuiper belt now moves in a path that rewrites the history of its adopted home. If one were to drift above Triton's surface, the experience would feel serene and haunting. The horizon would be sharp and pale, the sky nearly black even during the day. Frost would stretch across the plains, reflecting the faint sunlight in soft, powdery tones. In the distance, a plume of nitrogen might rise, silent and shimmering, before bending sideways in a gentle arc. The pattern it leaves on the surface would be a long, ruler-straight line of dark dust. Each texture would tell a story, of heat building beneath the crust, of pressures rising, of ancient materials shifting. Triton's beauty lies not in brightness or colour, but in quiet contradictions. It is cold, yet active, distant, yet dynamic, icy, yet possibly home to liquid water, deep below its nitrogen geysers, and smooth plains challenge the idea that faraway worlds freeze into stillness. Instead, Triton reveals a truth shared by many moons in the outer solar system. Where gravity, chemistry, and time come together, motion can arise even in the coldest places. Among Neptune's moons, Triton stands alone. It is larger, stranger, and far more active than any of its companions. It carries the history of a captured wanderer, the geology of a restless world, and the potential of an ocean hidden beneath its crust. It reminds us that moons need not be quiet, and that even in the far reaches of the solar system, a world can hold mysteries that glow with quiet intensity. Triton circles Neptune in darkness, but its story shines, etched in ice, carved by geysers, and written in the slow, patient movements of a captured world finding its place around a distant giant. Neptune is often celebrated for Triton, its strange icy companion with a captured past and an active surface. But orbiting alongside that dramatic world is a quieter family of smaller moons, dim, irregular bodies drifting through the blue glow of Neptune's distant realm. These moons do not erupt with geysers or carry hidden oceans. They do not draw attention with bright surfaces or dramatic features. Instead, they move softly around their planet, ancient and weathered, shaped by time and silence. Their stories are written in craters, shadows, and gentle motions, contributing to the quiet complexity that surrounds Neptune. The largest of these lesser-known moons is Proteus, a dark, irregular world that looks more like a battered rock than a polished sphere. Unlike round moons shaped by their own gravity, Proteus never became smooth enough to pull itself into a perfect form. Its surface is jagged and angular, carved by impacts that occurred over billions of years. Craters overlap like scars, each telling of collisions with stray debris drifting through the outer solar system. Because Proteus reflects only a small fraction of the light that reaches it, it appears as a shadowy object, dark grey, almost charcoal in tone, circling Neptune like a quiet sentinel. For such a large moon, it remains surprisingly unobtrusive, hiding its rough shape in the pale twilight cast by the distant sun. Farther out lies Naiad, a moon with a personality shaped by one of the most eccentric orbits in the entire solar system. Instead of a near-perfect circle, Naiad follows a path that stretches dramatically into space before swooping down close to Neptune again. This elongated orbit suggests that Naiad may have been disturbed long ago, perhaps when Triton was captured. Whatever its history, the result is a moon that experiences enormous variations in distance from Neptune, moving from far away to relatively close over the course of one long loop. Its surface is ancient, covered in craters that hint at a long life spent far from warmth or geological activity. When sunlight reaches Naiad, it illuminates a frozen, pitted landscape that has changed little for billions of years, preserved in the quiet grip of extreme cold. Closer to Neptune, several small inner moons drift quietly through the planet's shadowed region. Larissa is among them, a moon discovered decades ago but only truly understood when Voyager 2 captured its image. Like Proteus, Larissa is irregular in shape, formed from material that likely accreted around Neptune long ago. Its surface is marked by shallow craters and dark patches, giving it a weathered appearance that speaks of ancient collisions. Larissa's orbit is predictable and calm, guiding the moon through the inner system like a stone carried by a slow river. Nearby is Despina, a moon that orbits within Neptune's ring system. Because it moves so close to the planet, Despina plays a quiet but important role. It helps shepherd particles in the rings, influencing their motion through gentle gravitational pulls. Despina itself is small and heavily cratered, with a surface that seems to have been shaped by impacts and long-term erosion. Even though it is not a dramatic world, its presence helps maintain the faint arcs and delicate structures that define Neptune's rings. It drifts steadily, a guardian of fragile materials swirling in the planet's glow. Thalassa, another small inner moon, is even more irregular. Its shape does not resemble a sphere so much as a rounded block, as though it was once part of a larger body that fractured and reassembled. The surface is pocked and uneven, reflecting a long past without geological renewal. Thalassa orbits Neptune quickly, covering great distances in short times despite the dim sunlight. It appears as a small, dark object racing along the inner paths of the Neptune system, held tightly by gravity but moving with a quiet urgency. The most graceful relationship in this family, however, belongs to the pair of moons known as Naiad and Thalassa. These two small bodies share a remarkable orbital dance, one of the most unusual in the solar system. Instead of circling Neptune independently, they move in a coordinated rhythm that prevents them from ever colliding. Naiad's orbit lies slightly closer to Neptune, while Thalassa moves just outside. In most systems, this arrangement would lead to occasional encounters or instabilities, but here, the two moons weave around each other in a synchronized pattern that feels almost choreographed. The dance works because Naiad's orbit is tilted slightly relative to Thalassa's. Every time Naiad passes Thalassa, it does so from above or below, slipping past in a motion that resembles two threads crossing without tangling. Naiad completes a revolution more quickly, but the timing is so precise that whenever the two moons approach one another, Naiad is shifted in altitude, either higher or lower, so the two never meet. They glide along their paths like partners in a cosmic waltz, tracing curves that remain locked together by gravity's patient pull. This orbital pattern is called a resonant configuration, and in Neptune's system it forms something rare, a moving sculpture of motion and distance, a silent ballet performed in the dark. Naiad passes Thalassa every few hours, but always in such a way that the two remain separated, following paths that never intersect. If someone could observe them from a platform above their orbits, the motion would look like a gentle weaving. Naiad would appear to bob up and down relative to Thalassa, shifting with each pass, while Thalassa holds a steady course. The effect is calming, almost hypnotic, as though the moons are breathing in unison. These smaller moons, though often overlooked, contribute to Neptune's story in meaningful ways. Their gravitational interactions help maintain the stability of the inner system. Their dark surfaces and irregular shapes offer clues about the environment in which they formed. Their quiet motions complement the more dramatic features of Neptune's atmosphere, adding a sense of balance to the planet's complex world. They also highlight the diversity of moons in the outer solar system. Some are captured worlds with active surfaces, others are frozen relics with no internal motion. Still others play roles as shepherds and guides, maintaining ring structures or participating in resonances that shape their paths. The moons of Neptune together create a tapestry of motion: fast, slow, eccentric, circular, tilted, stable, carried out in the thin, dim light of a sun more than 4 hours away. Imagine drifting alongside them. The light would be faint, casting long, pale shadows across cratered surfaces. Proteus would pass like a massive dark stone etched with ancient lines. Nereid would glide in from far out, its elongated orbit bringing it slowly closer before carrying it away again. Larissa and Despina would move quickly, tracing arcs of darkness near the rings Thalassa would slip by like a rounded shard, and just above or below it, Naiad would float past with perfect timing, their paths never touching, their motions intertwined. Together they form a quiet family, companions to a giant circling silently through the cold and distance. They do not shine brightly, but their presence adds depth to Neptune's world. They create harmony among the rings, balance among the orbits, and a sense of gentle motion that complements the planet's turbulent atmosphere. In their quiet way, each moon contributes a thread to the fabric of Neptune's system, drifting through dim blue light with steady calm. These small moons remind us that beauty in the outer solar system is not always loud or dramatic. Sometimes it is found in the soft shadows of cratered surfaces, in the precise steps of orbital dances, and in the unspoken companionship of worlds moving peacefully around a distant planet. Their stories unfold slowly, in faint light and deep cold, offering glimpses into a realm where motion continues even where silence reigns. In the summer of 1989, a small, silent traveller arrived at the edge of the solar system after a journey that had lasted more than a decade. Voyager 2, having already swept past Jupiter, Saturn and Uranus, approached Neptune with the calm persistence of a spacecraft that had seen worlds unfold beneath it many times before. Yet even with all its experience, this final encounter carried a special stillness. Neptune stood far beyond the warmth of the sun, wrapped in deep blue clouds and drifting through a darkness so complete that sunlight arrived as faint silvery strands. As Voyager 2 drew closer, that distant world sharpened into view, quiet, cold, and unexpectedly alive. By the time Voyager 2 reached Neptune, the spacecraft was more than 4 billion kilometers from home. Signals from Earth took hours to reach it, and its replies returned only after their long, lonely flight back through the solar wind. There was no room for error. Every command had to be correct. Every observation had to count. And as the spacecraft approached the planet, its cameras opened a window into a realm no human had ever seen up close. The first images revealed Neptune's atmosphere in stunning detail, a blue so rich it seemed unreal, streaked with shifting clouds and swirling patterns. The faint haze that had made the planet look smooth from Earth dissolved under Voyager 2's gaze, exposing a world full of storms and motion. One of the most surprising discoveries was the Great Dark Spot, a vast storm nearly the size of Earth. It spun in the southern hemisphere like a shadow carved into the atmosphere, edged by bright methane ice clouds. The storm's sharp borders suggested a deep, powerful vortex, something that had grown in the cold darkness far from the sun. Nearby, Voyager 2 spotted a smaller bright feature racing around the planet. Scientists nicknamed it the Scooter Cloud. It darted across Neptune's face with remarkable speed, carried by winds that howled faster than sound. Those winds, measured for the first time during the flyby, swept through the atmosphere with a force that defied expectations. Even with so little sunlight to warm it, Neptune's atmosphere churned with incredible energy, driven by the heat rising from deep within the planet. As the spacecraft drifted closer, it turned its instruments toward the rings. From Earth, Neptune's rings had been nearly invisible, faint bands of dust and dark material that blended into the blackness of space. Voyager 2's proximity revealed their delicate beauty. The rings were thin, uneven, and marked by bright arcs, clumps of material that refused to behave like typical ring systems. These arcs, like Liberté and Égalité, clustered together in mysterious patterns, held in place by gravitational resonances with nearby moons. In the spacecraft's images, the arcs glowed faintly, like threads of smoke illuminated by a distant light. Voyager 2 continued on its path, slipping gracefully past Neptune and preparing for its encounter with Triton. As it approached the moon, the landscape transformed once more. Triton appeared pale, icy, and strangely smooth, its surface almost devoid of craters. The pictures revealed patterns that looked like frozen lakes, ridges that curled like fingerprints, and vast plains shaped by processes that seemed too active for such a cold place. Then came the discovery that surprised even the mission team. Triton was erupting. Dark streaks across the surface marked the paths of nitrogen geysers, jets shooting several kilometers into the thin atmosphere before bending sideways in the gentle winds Voyager 2 captured these plumes in real time. Proof that Triton was alive with geological activity. It was a world reshaped by internal heat, not a frozen relic, but a dynamic moon that breathed through icy cracks. Each new image, each measurement, each silent frame of data returned from the spacecraft felt like a small miracle. Neptune's deep blue became clearer. Triton's icy plains unfolded. The shadows in the rings sharpened. The storm patterns shifted. And on Earth, scientists and engineers gathered around screens, waiting hours for each signal to arrive, knowing they were watching scenes no human eyes had ever witnessed. The distance was so great that every picture captured by Voyager 2 represented a moment frozen in time, already 4 hours old by the time it reached Earth. There was something profoundly emotional in the quiet way those images arrived. Voyager 2 did not shout or announce itself. It simply transmitted the light it had gathered. Frame by frame, the spacecraft revealed a world that had been little more than a blue dot for centuries. Its discoveries extended far beyond scientific insight. They carried a sense of wonder, a reminder that even at the far edge of the sun's influence, planets move with beauty and rhythm. As the spacecraft flew past Neptune, its trajectory carried it on a downward arc behind the planet, slipping into the shadows before emerging again on the other side. During that passage, the cameras captured Neptune lit from behind, a crescent of glowing blue air edged by sunlight scattering through the upper atmosphere. The arc looked delicate, like a whispered outline of the planet's shape, glowing with ethereal softness. It is still considered one of the most hauntingly beautiful images ever taken in planetary exploration. Voyager 2's instruments recorded temperature gradients, measured magnetic fields, mapped winds, traced radiation belts, counted particles, and watched shadows drift across the cloud tops. It was a full exploration, a careful study unfolding in silence as the spacecraft swept past at enormous speed. And then, almost before the encounter had settled into the minds of those watching from Earth, Neptune began to recede. The spacecraft continued on its path, leaving behind the blue world and its moons, carrying the final direct observations of a planet no mission has returned to since. As Neptune shrank into the distance, Voyager 2 turned its antennas toward Earth one last time to transmit the final data from its encounter. The messages arrived slowly, taking hours to cross the darkness. Yet each bit carried the weight of discovery from a place so remote that sunlight itself seemed tired when it reached the atmosphere. For many who had worked on the mission, the moment was bittersweet. Voyager 2 had completed the grand tour of the outer planets, an achievement never repeated. It had shown the world that Neptune was not a quiet, distant sphere, but a dynamic, complex planet full of movement. The winds, storms, arcs, and geysers revealed a system alive with contrasts and energy, and though the spacecraft carried no eyes and no ears, it had acted as a traveller for everyone on Earth, drifting through the outer darkness on behalf of all who wondered. The memory of that encounter lingers like a soft echo, A small spacecraft, no larger than a car, drifting past a distant planet bathed in blue, surrounded by faint rings and icy moons. A silent visitor returning pictures across billions of kilometers. A moment when the outer solar system opened itself for just a little while, revealing its secrets before closing its doors again. Voyager 2 continued onward into the deep, leaving Neptune behind. Its flyby remains one of the most graceful moments in space exploration. A quiet passing, a gentle revealing, a journey illuminated not by noise or spectacle, but by the soft blue glow of a planet touched lightly by sunlight at the edge of the solar system. Neptune turns through space with an elegant tilt, leaning on its axis by a little more than 28 degrees. This angle is similar to Earth's and suggests that Neptune too experiences seasons. But on a world so far from the Sun, seasons are not measured in months or years. They unfold over decades, shifting so slowly that a single season could last longer than a human lifetime. The planet's distant orbit stretches each journey around the Sun to nearly 165 Earth years, and with that vast sweep comes an atmosphere shaped by time rather than quick weather cycles. Neptune's seasons drift like long breaths, each one lingering, expanding and dissolving with quiet patience. Because Neptune is so far from the Sun, the light that reaches it arrives faint and diffuse, more like a pale glow than a brilliant radiance. Even at noon, the sunlight would resemble the soft lighting of early evening on Earth. When this faint light shifts across Neptune's surface due to the planet's axial tilt, the effect is subtle but far-reaching. The hemispheres alternate between long, slow periods of gentle illumination and long, slow periods of dimming. The difference is not dramatic in brightness, but it influences the temperature and circulation patterns throughout the atmosphere. Neptune responds not with rapid swings, but with gradual transformations that echo across years. During a Neptunian season, clouds and storms adjust their behavior, guided by the slow drift of sunlight. In the hemisphere tilted toward the Sun, methane ice clouds may brighten slightly, as faint warming encourages condensation, while the opposite hemisphere cools even further, allowing deeper cloud layers to rise or fall. These changes do not happen quickly. Instead, they ripple through the atmosphere like waves stretching across an ocean of time. Each shift influences the next, creating patterns that can last for decades before giving way to something new. Astronomers watching Neptune from Earth have observed these long seasonal variations as gentle shifts in brightness and cloud formations. Over years, the planet's features subtly rearrange themselves, building bright bands in one hemisphere while darkening regions in the other. These cycles are slow and serene, with storms appearing more frequently at certain points and fading during others. The changes resemble tides moving through the sky, gradual, rhythmic, and far too slow to watch unfold moment to moment. Yet when decades of observations are compared, the difference becomes unmistakable. Neptune's atmosphere is breathing through seasons that stretch across generations. One of the most fascinating effects of Neptune's seasons is the behavior of its storms. Some storms strengthen as the hemisphere tilts toward the Sun, drawing energy from small increases in temperature or from shifting circulation patterns. Others weaken, shrink, or dissolve. Over many years, bands of clouds may migrate north or south by thousands of kilometers, guided by the invisible hand of the planet's rotation and sunlight. Researchers have documented bright cloud patches appearing suddenly in mid-latitudes, then dispersing as the atmospheric balance shifts again. These events unfold so slowly that each observation becomes a snapshot of a story that can be understood only when viewed over decades. Imagining Neptune's seasons is like imagining time slowed to a crawl. The blue and white patterns drifting across its surface do not rush or swirl with the urgency of Earth's storms. Instead, they move with the grace of a glacier, shifting so gradually that the changes appear almost static over any short period. If a person could stand above Neptune and watch it for years, they would see the atmosphere brighten here, darken there, twist slightly, spread gently, and then settle again. It would be like watching the shadows of clouds pass across a field, but stretched out over the length of a lifetime. The planet's axial tilt means that each hemisphere faces the sun for decades before turning away. When one hemisphere enters summer, the other slips into winter, with each season lasting more than 40 Earth years. Summer brings small increases in sunlight, which can alter the temperature of the upper atmosphere enough to encourage storm activity or drive subtle changes in the height of cloud layers. Winter brings deeper cold, reinforcing the formation of high-altitude hazes and shifting the behavior of lower clouds. These changes appear faint in individual images, but when viewed as a sequence across decades, the atmosphere reveals its slow, patient transformations. Because Neptune emits more internal heat than it receives from the Sun, its seasons interact with a constant stream of energy rising from below. This internal heat drives much of the planet's dynamic weather, including its fast winds and turbulent storms. But the seasonal shifts guide where and how that internal energy is expressed. During a long summer, certain atmospheric layers may warm just enough to change the balance between rising and sinking air, altering circulation patterns on a global scale. During the long winter, the opposite occurs, leading to changes in the distribution of storms, cloud belts, and atmospheric structures. The seasons do not overpower Neptune's internal heat, but they work in harmony with it, shaping the slow rhythm of the planet's outer layers. As the decades pass, the subtle interplay of sunlight and internal heat produces patterns that resemble broad brushstrokes of colour across Neptune's surface. Bright methane clouds may cluster in mid-latitudes during certain seasonal phases, drifting across the blue background like soft white feathers. In another season, the cloud tops might thin, allowing deeper, darker blues to emerge. The variations create the impression of a living canvas, one that changes not in hours or days but in long, quiet intervals. If one could drift high above Neptune's cloud tops, the view would be tranquil. Broad fields of blue would stretch across the horizon, broken here and there by streaks of white, perhaps a bright storm, perhaps a patch of methane ice drifting in silent formation. Over months, those streaks might drift slightly north or south. Over years, entire bands might shift. Over decades, the balance between bright and dark regions would tilt slowly from one hemisphere to the other, reflecting the planet's steady march through its enormous orbit. During the late 1990s and early 2000s, astronomers using the Hubble Space Telescope documented changes in Neptune's brightness that hinted at the progression of its seasons. The planet grew subtly brighter in the southern hemisphere as it moved through its long summer, possibly due to changes in cloud structure and methane distribution. Later, as Neptune approached its farthest point from the Sun, these patterns shifted again, suggesting the turn toward autumn. Each observation, spaced by years, added a new chapter to Neptune's seasonal narrative. Unlike Earth, where seasonal changes drive dramatic swings in temperature, Neptune's distance from the Sun means its seasons are defined more by slow, atmospheric reorganization than by warmth or cold. The planet remains frigid throughout the year, but the way that frigid atmosphere moves, brightens, and rearranges itself depends on the gentle tilt of its axis and the long, gliding curve of its orbit. This extended timeline means that no single generation will ever witness Neptune complete a full seasonal cycle. A person born at the beginning of one Neptunian spring would not live long enough to see the next spring return. Instead, the seasons are experienced by humanity as a collective project, understood through observations passed down and combined over centuries. Each astronomer contributes a chapter, adding to the understanding of a story too long for any single life to comprehend fully. Yet even at this immense timescale, Neptune's seasons offer a sense of calm. They remind us that time in the outer solar system moves differently. It does not rush forward in bursts of change. It flows like a slow river, shifting the landscape quietly. The planet's blue and white features drift through time with a serene composure, painting a picture of a world shaped not by haste, but by the patient interplay of light and darkness. In the dim glow of distant sunlight, Neptune turns, carrying its seasons through the centuries. Clouds brighten and fade, storms rise and fall, patterns drift across its surface with the pace of long shadows crossing an endless sea. And in that slow, steady motion lies the beauty of a world defined by time, time stretched, softened, and allowed to unfurl without hurry, under the gentle guidance of a sun that shines like a distant lantern across the cold blue expanse. In the early days of the solar system, long before Neptune settled into its distant orbit of deep blue silence, the giant planets moved through a landscape far more chaotic than the elegant arrangement seen today. The young sun was surrounded by a vast disk of gas, dust, and icy bodies. Within that disk, Jupiter, Saturn, Uranus, and Neptune drifted gradually. Tugged by countless gravitational whispers, Neptune did not begin life in the cold outer darkness. Instead, evidence suggests it formed much closer to the Sun before slowly migrating outward, carried along by the shifting tides of planetesimals and ancient resonances. That slow journey reshaped the outer solar system, sculpting the Kuiper belt and scattering countless bodies into new orbits. To imagine this early era, picture a crowded region filled with icy fragments ranging from grains of dust to objects hundreds of kilometers across. These planetesimals orbited the young sun in dense swarms, colliding, merging, and drifting. The young Neptune moved among them, interacting gravitationally with each passing body. Sometimes, Neptune's pull would fling a small object outward into a wider orbit. Other times, the interaction would send an object inward, deeper into the planetary region. Each encounter carried its own momentum exchange, and over millions of years these exchanges acted like tiny pushes. With each outward scattering, Neptune absorbed a slight inward tug. With each inward scattering, it gained a small outward push. The balance ultimately favoured outward motion. Slowly but steadily, Neptune drifted away from the Sun. This migration was not a smooth glide. It occurred during a period of planetary instability, a time when the orbits of the giant planets shifted dramatically. A leading model known as the NICE model describes how interactions among Jupiter, Saturn, Uranus, and Neptune generated a domino effect. When Jupiter and Saturn crossed a gravitational resonance with each other, their combined gravity destabilized the orbits of the outer ice giants. Uranus and Neptune were nudged into sweeping arcs, during which Neptune moved outward, displacing countless icy bodies from its path. These displacements rippled through the solar system like waves, spreading from a single stone thrown into water. As Neptune migrated outward, it became the architect of the Kuiper Belt, a broad region of icy objects that now orbits beyond the planet. Before Neptune's migration, the outer disk likely contained far more material, arranged in a more tightly packed configuration. Neptune's gravitational influence scattered many of these objects. Some were thrown outward into highly elongated orbits, forming what would eventually become the scattered disk. Others were captured into stable resonances with Neptune, meaning their orbital periods settled into simple ratios with the planets, like 2 orbits of a smaller body for every 3 orbits of Neptune. These resonances act like cosmic metronomes, keeping objects in long-term harmony with the giant planet's motion. One of the most famous examples is Pluto, which resides in a 3:2 resonance with Neptune. Despite crossing Neptune's orbital path, Pluto never collides with the planet because the resonance keeps both bodies in a stable dance, each orbit timed to avoid close encounters. This resonance likely formed during Neptune's outward migration, as the planet swept through regions filled with small bodies. Instead of scattering all of them, Neptune captured some into resonances where they remained, safe, stable, and locked into cosmic rhythm. Not all bodies were so fortunate. Many were flung outward entirely, becoming part of the distant scattered disk or even the inner Oort cloud. Some may have been ejected from the solar system altogether, wandering through interstellar space as planetary castaways. Each scattering event represented a small exchange of energy, another infinitesimal nudge that helped Neptune climb to its present orbit. The process unfolded over billions of years, shaping not just the Kuiper Belt but also the architecture of the giant planets themselves. Throughout this journey, Neptune's gravity acted like a sculptor's tool, carving structure out of chaos. It created gaps and clusters, sweeping some regions clean while populating others with captured bodies. The Kuiper Belt that exists today contains families of objects whose orbits bear the imprint of Neptune's ancient passage. Some remain trapped in resonances, their motions synchronized across billions of years. Others occupy stable, classical orbits that lie just beyond Neptune's influence. Still others inhabit peculiar tilted paths that hint at long-ago close encounters. To understand how Neptune created these patterns, imagine the early solar system as a wide, shallow pool filled with small floating objects. A large object passing through the pool, like Neptune migrating outward, would create wakes, pulling some objects along while pushing others aside. Those caught in the right position might fall into step with the giant's motion. Those in less fortunate positions would be flung outward, left behind, or redirected entirely. Neptune's migration produced ripples of gravitational influence that reshaped the entire pool. One of the most intriguing effects of this process is the existence of resonant populations beyond Pluto. Objects in the 2:1 resonance, for example, orbit the Sun twice for every 1 orbit of Neptune. These distant bodies remain in stable positions because Neptune's gravity periodically nudges them back into alignment. The gentle yet persistent repetition of these interactions keeps their orbits predictable. It is a quiet but powerful form of control, expressed not through force but through rhythm. The story of Neptune's influence is not limited to the creation of resonant bodies. Its gravitational scattering sent shock waves through the outer solar system that may have triggered the late heavy bombardment. a period when countless asteroids and comets rained down on the inner planets, leaving craters still visible today. As Neptune moved outward and destabilized the outer disk, swarms of icy bodies were redirected inward. Many collided with Earth, the Moon, and the rocky planets, delivering both destruction and, perhaps, vital materials like water and organic compounds. Neptune's migration may have helped shape Earth's early environment in ways that influenced the development of life. Over time, as the giant planets settled into their final orbits, the outer solar system quieted. The scattering slowed. The resonances stabilized. The Kuiper belt became a calmer region, filled with the remnants of the early chaos. But the structure Neptune left behind remains one of the most powerful pieces of evidence for its wandering past. The tilted orbits, the clustered resonances, the distant scattered objects, they are all fossils of motion, preserved not in rock but in orbital paths. Imagine watching this history unfold from a vantage point far above the young solar system. Neptune would appear as a glowing orb drifting outward, followed by shimmering clouds of icy fragments. Disturbed by its passage, objects would stream past the migrating planet, some falling into neatly timed orbits, others slingshotting outward into the dark. With each passing million years, the architecture of the solar system would become clearer, shaped by the silent interplay of gravity and motion. As Neptune found its place in the distant reaches, the system slowly settled into the arrangement we know today. The planet became a quiet guardian of the outer regions, its wandering days long past. Yet its influence lingers in every corner of the Kuiper belt, carried in the orbits of countless icy worlds that still drift under the patterns Neptune set in motion billions of years ago. Through this ancient, graceful process, Neptune helped turn chaos into harmony. Its migration wrote the outer chapters of the solar system's story, sculpting a landscape of resonances, scattered bodies, and quiet stability. In that story, Neptune stands not only as a distant blue world but also as a guide, one whose early journey shaped the paths of countless smaller worlds still drifting through the dim blue light of the sun's farthest frontier. Neptune may drift in the distant quiet of our solar system, but its story reaches far beyond its own orbit. In recent decades, as astronomers have discovered planets around other stars, a surprising pattern has emerged. Many of these distant worlds fall into a category that mirrors Neptune in size and composition. Some orbit far from their stars, remaining cold and dim. Others circle much closer than Neptune ever could, becoming warm or even blisteringly hot. These warm Neptunes and hot Neptunes appear frequently in the catalogues of exoplanets, making Neptune not just a solitary blue companion at the edge of our system, but a blueprint, an archetype, for a vast family of planets scattered throughout the galaxy. When astronomers first began finding planets around other stars, they expected to see rocky worlds like Earth, or gas giants like Jupiter. Instead, one of the most common types turned out to be planets roughly the size of Neptune, intermediate giants wrapped in thick atmospheres, many circling their stars in orbits far smaller than Mercury's. The diversity among these planets is striking. Some are close enough to their stars that their atmospheres simmer under intense radiation. Others lie in cooler regions, where temperatures allow clouds to form from exotic materials. These worlds are cousins to Neptune, but they live in environments Neptune never experienced. To understand these distant planets, scientists often begin with what is known about Neptune. Although Neptune is cold and far from the Sun, Its size, composition, and atmospheric behavior offer a foundation. Its atmosphere is dominated by hydrogen and helium, with methane shaping its color and chemistry. The upper layers form hazes, clouds, and storms that respond to subtle shifts in sunlight and internal heat. These features help astronomers model how similar atmospheres might behave when exposed to different conditions. For a hot Neptune orbiting close to its star, sunlight might strip away hazes, heat the upper atmosphere, or break apart molecules. For a warm Neptune, clouds might form from silicates, metals, or unfamiliar compounds. The underlying physics, pressure, temperature, and chemistry remain anchored to what began as Neptune's story. Hot Neptunes present some of the most intriguing mysteries. Many have atmospheres heated to extreme temperatures, where molecules rise, expand, or evaporate into space. Some show signs of atmospheric escape, trailing gas behind them like long, invisible comets. These planets challenge the assumption that Neptune-like worlds remain stable. Instead, they show that when placed near a star, a Neptune-mass planet can transform dramatically. Its atmosphere is shaped by radiation and stellar winds. Understanding how Neptune's own atmosphere interacts with cold, thin sunlight helps scientists scale those interactions to much more intense environments. Warm Neptunes, orbiting slightly farther out, reveal another side of this planetary family. These worlds may host clouds made from unexpected materials, tiny grains of silicate, droplets of exotic liquids, or mixtures of metals and volatiles. The temperature and pressure ranges in these atmospheres depend heavily on distance from the star, but the underlying structure often resembles Neptune's layered atmosphere, with deep mantle regions and thick outer shells of gas. When astronomers interpret the spectra from these distant worlds, light filters through their atmospheres. They compare the patterns to what Neptune teaches about scattering, absorption, and atmospheric chemistry. Neptune also provides insight into how these exoplanets formed. Its own history suggests that intermediate mass planets form naturally from the disk of material surrounding a young star. Neptune's composition reflects a mixture of gas, ice, and rock that accumulated during the solar system's early days. Many exoplanets appear to have followed similar paths, forming from the same kinds of building blocks, but ending up in different environments due to migration or gravitational interactions. Warm Neptunes near their stars may have started farther out, drifting inward during the chaotic phases of their system's early evolution. Hot Neptunes could be the remnants of larger gas giants that lost their outer layers, leaving behind a planetary core wrapped in a thin but heated atmosphere. One reason Neptune-like planets appear common is that the universe seems to favour their formation. They require enough material to grow beyond a rocky core, but not so much that they become gas giants. This balance is easy to achieve in many protoplanetary disks. Some planets accumulate more gas and grow into Jupiter-like giants. Others gather less and remain Earth-sized. But the middle ground, Neptune-sized worlds, often forms naturally, emerging as stable, long-lasting planets that can survive a wide variety of stellar environments. From the perspective of distant observers, Neptune would itself appear as a classic exoplanet type, a medium-sized world wrapped in hydrogen and helium, orbiting near the edge of its star's habitable zone. Its atmospheric signatures, methane absorption, scattering of blue light, traces of clouds, would stand out in the spectrum. If an alien civilization used the same tools astronomers use today, they might study Neptune not for its distance from the Sun, but for its composition, temperature, and chemical fingerprints. Those fingerprints would help them understand their own warm or hot Neptunes, just as we use Neptune to decode the distant worlds around other stars. One of the most calming reflections about Neptune's role is how quietly significant it has become. It is not the brightest planet, nor the largest. It does not dominate the night sky. And yet, it sits at the crossroads of our understanding of exoplanets. Every time astronomers study a Neptune-sized world in another system, they lean on what Neptune teaches us about atmospheres under pressure, about mantles made of volatile materials, about chemistry shaped by distance from a star. Neptune's storms provide templates for the storms of warmer worlds. Neptune's clouds offer analogies for clouds made of unfamiliar compounds. Neptune's slow seasons, faint sunlight, and deep interior help shape the models that describe entirely different environments. As instruments improve and telescopes grow more advanced, scientists are beginning to map the atmospheres of exoplanets with increasing clarity. They look for water vapor, methane, carbon monoxide, and exotic molecules. They measure temperatures and wind speeds. They trace the silhouettes of planets as they pass in front of their stars, collecting hints about how their atmospheres scatter the starlight. And behind these interpretations lies Neptune, a quiet guide reminding us how gas and ice behave under different pressures and temperatures. Future missions may reveal even more. As spectral resolution increases, researchers will compare Neptune's atmospheric fingerprints to those of distant worlds, searching for patterns that match or deviate. In those comparisons, Neptune becomes a standard, a reference point. It helps answer questions such as, why do some warm Neptunes retain thick atmospheres while others lose them? How do internal heat sources shape weather on planets far from or close to their stars? What happens when Neptune-like planets migrate inward? What kinds of chemistry emerge in atmospheres with similar compositions but wildly different environments? The answers will not come from distant worlds alone. They will come from Neptune, the planet that drifts in quiet cold yet carries within it a wealth of knowledge about how intermediate giants form, evolve, and behave. In this way, Neptune becomes a bridge between our own solar system and the vast, diverse collection of planets orbiting other stars. In the gentle glow of its blue atmosphere, Neptune holds a blueprint written in winds, clouds, and chemistry. That blueprint stretches outward into the galaxy, connecting worlds near and far. It reminds us that even in the distant reaches of our own system, the clues to understanding the greater cosmos can be found. Neptune is not only a world to be observed, it is a world that teaches, a world that reflects patterns repeated across countless systems. Its calm, drifting presence becomes a guide for decoding the mysteries of exoplanets, helping us read the stories written in the atmospheres of worlds we've never seen up close. Through Neptune, we learn that the universe repeats itself in broad strokes. Warm Neptunes, hot Neptunes, cool Neptunes, they all echo the same fundamental principles, and in that sense, Neptune's role extends far beyond its orbit. It becomes a key, unlocking the secrets of distant worlds that shine faintly in the light of suns scattered across the galaxy. The future of Neptune exploration begins not with rockets or engines, but with quiet ideas. Plans drafted in laboratories, hopes whispered through meeting rooms, and visions of spacecraft drifting through the deep blue light of a world no human has yet seen up close. Neptune sits so far from the Sun that any mission must travel for more than a decade before it even arrives. Yet despite the distance, scientists continue to imagine orbiters, atmospheric probes and landers that could someday reveal the secrets hidden beneath the planet's clouds and within the icy worlds that circle it. These future missions would push deeper into the unknown than any spacecraft has gone before, opening a new chapter in the story of the outer solar system. A flagship mission often discussed is a Neptune orbiter, an enduring explorer that would spend years circling the planet, studying its atmosphere, rings, moons, and magnetic field with gentle persistence. Unlike Voyager 2, which flew past Neptune in a single sweeping arc, an orbiter would remain in place. It would drift above the cloud tops, mapping the winds, watching storms form and dissolve, and tracing the faint arcs of the rings as they shift under the influence of shepherd moons. Its instruments could peer into the atmosphere layer by layer, revealing the temperatures, pressures, and chemical signatures hidden beneath the soft blue glow. For the first time, scientists could watch Neptune's long seasons unfold in real time, capturing changes that take years rather than hours. Alongside an orbiter, many mission proposals include an atmospheric probe, something small, sturdy, and built to survive a descent through Neptune's cold, high winds. Released from the orbiter, the probe would fall slowly through the upper atmosphere, sampling gases as it drifts into deeper layers. It would measure the abundance of hydrogen, helium, and methane, and search for trace compounds that might reveal how the planet formed. As it sinks lower, the probe could study the temperature gradient, the transition zones between clouds, and the structure of the layers that shape Neptune's storms. Although the probe would only transmit for a short time before pressure silences it, the data gathered during its descent would offer a glimpse into regions no telescope could ever reach. But perhaps the most captivating idea for future exploration is a mission dedicated to Triton, Neptune's largest moon and one of the most intriguing objects in the solar system. Triton's retrograde orbit, nitrogen geysers, smooth plains, and possible subsurface ocean make it a target worthy of detailed exploration. Scientists dream of a Triton lander, a machine that could drift gently onto the moon's icy surface and study its chemistry, geology, and atmosphere up close. It could examine the dark streaks created by geyser eruptions, analyze the nitrogen frost, and search for the fingerprints of active processes beneath the crust. Some proposals even imagine a hopper, capable of leaping short distances to sample multiple regions of the moon, its frozen plains, fractured ridges, and darkened, streaked areas shaped by erupting plumes. A Triton orbiter would complement such a lander beautifully. It could watch geysers erupt in real time, measure the moon's tenuous atmosphere, and search for subtle wobbles in Triton's orbit that might hint at a hidden ocean below. By studying how Triton flexes and shifts, scientists could infer the thickness of its ice shell and the depth of any liquid layer beneath. Such discoveries would reshape our understanding of icy moons, planetary capture, and the chemistry of distant ocean worlds. Beyond Triton, Neptune itself holds countless unanswered questions. A future mission could investigate the planet's internal structure, determining how heat rises from its core and how exotic ices behave under immense pressure. Instruments might detect the depth and behavior of supersonic water, the form of matter that may dominate Neptune's mantle. They could trace how ions drift through the rigid lattice of oxygen atoms, creating electrical currents that feed the planet's tilted magnetic field. Understanding these exotic states of matter would have implications far beyond Neptune, offering insight into the physics of giant planets across the galaxy. The stability of Neptune's rings is another mystery waiting to be explored. An orbiter could watch the faint arcs change, perhaps even observing particle collisions or interactions with nearby moons in real time. It could track the shepherd moon Galatea as it sculpts the Adam's ring, and watch how dust flows from one region to another. Over years, the spacecraft could build a complete picture of how these delicate structures survive in a region filled with gravitational currents. Travelling to Neptune requires patience on a scale rarely demanded of planetary exploration. Even with powerful rockets and favourable alignments, a mission might take 12 to 15 years to reach the distant world. The spacecraft would spend that time drifting steadily outward, crossing the orbits of Mars, Jupiter and Saturn before reaching Uranus and continuing on. For most of the journey, the spacecraft would glide in near silence, powered by steady pulses from its engines and guided by commands sent across billions of kilometers. Engineers and scientists on Earth would wait through long stretches with little activity, knowing that the moment of encounter, years in the making, would be brief compared to the voyage itself. This patience is part of the beauty. Neptune embodies distance, calm and quiet transformation. Any spacecraft sent there must embrace the same rhythm. It must drift gently toward the blue horizon, carrying instruments designed to survive the coldest reaches of sunlight. For those working on such missions, the commitment spans decades. Some scientists who helped design the spacecraft may retire before it arrives. Others may hand their work to the next generation, who will be the ones to witness the first close-range images of Neptune since Voyager 2. Yet that long waiting period is also what makes the journey so meaningful. Imagine a spacecraft approaching Neptune after more than a decade of travel. The planet would appear first as a star, then as a disk, then as a world of deep blue texture. Clouds would sharpen into view. Storms would reveal themselves. Moons would become bright points of light, moving slowly against the blackness. Then, finally, the spacecraft would slip into orbit, circling the planet in graceful arcs, gathering data and sending home images stitched from faint light. Those images would travel across the solar system for hours, each signal carrying the weight of discovery. When they arrived on Earth, they would show Neptune once again as a place of storms, arcs, shadows, and secrets. For the first time, we would watch its atmosphere change over years rather than hours. We would see the rings shift, Triton breathe, and the magnetic fields sweep around the planet like the glow of invisible ribbons. Future missions would not simply revisit Neptune, they would deepen the story. They would reveal details that Voyager 2 could only hint at. They would connect Neptune to the growing knowledge of exoplanets, helping place our own system within the broader context of the galaxy. They would teach us about oceans beneath ice, about exotic forms of matter, about weather systems shaped by faint sunlight, and about the physics of magnetic fields born far from iron cores. And through it all, the spacecraft would drift quietly, following its path around a world bathed in blue. In the stillness of deep space, illuminated by a sun that shines more like a distant lantern than a blazing star, the future of Neptune exploration would unfold gently. Each discovery would feel like a soft whisper across billions of kilometers, a reminder that even at the far edge of the sun's reach, there is wonder waiting for those willing to travel the long road outward. The horizon around Neptune is calm and delicate, touched by storms below and faint starlight above. One day, a spacecraft will approach that quiet boundary once again, gliding toward a world that has waited patiently for our return. Neptune drifts at the farthest edge of sunlight, where the warmth of the sun fades into a pale glow and time seems to stretch into something slower, softer, and more patient than anything found closer to home. It is a world wrapped in deep blue light, a shade so rich and calm that it feels less like a planet and more like a dream suspended in space. Across its surface, storms the size of continents rise and fall without sound. Winds race faster than anything on Earth. Thin, dusty rings form faint ribbons around the planet, barely visible even to the sharpest eyes, and circling in wide, gentle arcs are moons of every character. From Triton, with its nitrogen geysers and hidden possibilities, to quiet companions like Proteus and Nereid, drifting like small stones in a vast cosmic tide. Everything about Neptune invites reflection. It sits so far from the sun that light arrives as a soft whisper, illuminating the atmosphere in delicate tones noon resembles twilight. Shadows stretch longer, colours deepen, and in this muted light, Neptune carries both motion and stillness, turbulence and calm. Its storms churn with incredible force, yet from afar they look serene, like swirling patterns beneath still water. Its magnetic field tilts and shifts in ways that seem almost artistic, weaving invisible lines around the planet. And through it all, Neptune radiates more warmth than it receives, a quiet glow rising from the depths as though the planet carries a small ember of its early history deep inside. Beyond its atmosphere, the rings circle like dust caught in a slow dance. They are not bright or bold. Instead, they feel like soft accents, reminders that even at the farthest frontier of our solar system, structure and rhythm persist. Some of the ring arcs cluster together as though held by unseen hands, guided by the gentle pull of small moons drifting nearby. It is a system held together by gravity, history, and the silent choreography of countless small worlds interacting across vast distances. Triton, the captured wanderer, remains one of Neptune's greatest mysteries. With its retrograde orbit, icy plains, erupting geysers, and possible hidden ocean, it offers a glimpse into processes that unfold far from sunlight. The smaller moons, with their ancient craters and quiet paths, provide contrast. Tiny, steady companions moving through the faint blue glow. Together, they shape a world that feels complete in its silence, where every moon and ring contributes a small note to the larger harmony. To look at Neptune is to gaze into the mixture of calm and motion that defines the outer solar system. It is a reminder that beauty does not always announce itself loudly. Sometimes it is found in the dimmest light, in the slowest patterns, in the quiet persistence of forces shaping worlds over billions of years. Neptune embodies that quiet beauty. It stands at a distance where the sun no longer dominates, where space becomes colder and shadows deepen, and where the universe begins to feel both immense and intimately peaceful. As future missions drift toward Neptune's horizon, they will find a planet that rewards patience. They will see storms evolve over decades, rings shift with subtle precision, and moons reveal secrets carved into ice. They will listen to the faint signals rising from deep below the clouds, signals shaped by exotic materials found nowhere on Earth. Neptune will not reveal everything at once. It never has. But it will offer its mysteries gently, in soft layers, much like the blue atmosphere that wraps around it. In the quiet blue frontier of Neptune, the universe invites us to slow down, to breathe, to notice the things that move at their own pace, drifting clouds, ancient orbits, long seasons. It is a world that reminds us that the cosmos is not only made of blazing stars and violent events, it is also made of silence, of cool light, of slow and steady transformation happening far beyond our sight. And as you drift with these thoughts toward rest, imagine Neptune turning slowly beneath the distant sun, its blue surface shimmering, its storms whispering, its moons gliding in calm arcs, a world of mystery held in quiet light. May your night be as peaceful as a journey through Neptune's deep blue calm, and may sleep find you gently,